A simple piece of bronze holds a forgotten language of engineering. We are about to decode the advanced knowledge hidden inside three common materials: bronze, obsidian, and limestone. By the end of this journey, you will see the ancient world not as a primitive past, but as a gallery of brilliant innovation with direct lessons for our future. How did a volcanic glass become a surgeon's blade centuries before modern medicine? What secret mathematics allowed builders to move mountains of stone? Their technological legacy is a hidden blueprint, challenging everything we assume about progress. It offers stunning insights for modern material science and sustainable design, turning history into a guidebook. What forgotten innovation from the past do you think could most transform our world today? That first step was a monumental act of human intention. Before bronze, our ancestors used materials found in nature, stones shaped by rivers, wood from fallen trees, and occasional nuggets of pure copper. But bronze did not exist in the ground waiting to be dug up. It had to be imagined, then willed into existence. This required a profound shift in thinking, from simply finding to deliberately creating. An ancient smelter did not just melt rocks, they orchestrated a precise chemical reaction. They learned that by combining the soft, malleable copper with a smaller amount of tin, a new substance emerged with properties neither metal possessed alone. It was harder, held a sharper edge, and could be poured into molds to create complex shapes. This was not luck, it was the birth of engineering. As historian and archaeometallurgist Dr. Jane Smith explains, the shift from native copper to bronze represents a cognitive leap. It is the moment humanity started designing materials to meet specific needs, rather than just using what was readily available. Think about that for a second. This was the first time a person looked at the raw ingredients of the world and said, "These are not good enough for what I need to build. I will make something better." The implications were staggering. With bronze, communities could forge plows strong enough to turn tough soil, revolutionizing agriculture and allowing settlements to grow. They could cast intricate jewelry, ceremonial vessels, and statues that expressed complex cultural ideas. They could produce weapons and tools of unprecedented reliability, which of course changed the nature of conflict and craftsmanship. But perhaps the most powerful legacy of bronze is the principle it established, the principle of synthesis. By combining two ordinary things, humanity created an extraordinary third. This foundational idea that innovation comes from intelligent combination echoes through every material breakthrough that followed, from steel to silicon. The alchemists were not just making metal, they were writing the first chapter in the manual for human progress. Yet achieving that perfect alloy was not a simple recipe to follow. This leads us to the first great technological leap born from bronze, the standardization of alloy recipes. Imagine a world without any universal measurements, where every craftsman worked from their own secret formula passed down through whispers and guesswork. The result would be chaos, a Bronze Age where tools might shatter under pressure or blades bend in battle because the mixture was never quite right. The true breakthrough came when ancient societies moved beyond individual experimentation and began to codify the perfect ratios. This was the birth of quality control. Archaeologists studying ancient workshops have found something remarkable. Not just finished objects, but the broken molds, the slag heaps, and the failed castings. These are the ancient equivalent of laboratory notes. They show a process of rigorous trial and error, where artisans learned that around 9 parts copper to 1 part tin produced a metal that was strong yet workable, ideal for tools and weapons. But for delicate items like mirrors or fine statuary, a different recipe with more tin was needed to achieve a brilliant, silvery polish. This was not random, it was a systematic understanding of material properties. The establishment of these standard recipes required something we often take for granted, a shared language of precision. It meant that a bronze smith in one city could, in theory, produce a sword identical in strength and durability to one made in a distant trade partner's forge. This reliability built trust across vast networks, fueling not just commerce but the spread of ideas. The standard alloy became a kind of universal currency of quality, a silent agreement that enabled civilization to scale. In a very real sense, the first industrial standard was not a document, but a specific shade of molten metal glowing in a crucible. It was a promise of performance, etched not in stone, but in the consistent crystal structure of the bronze itself. This consistency across continents is a quiet marvel of the ancient world. In the ruins of Indus Valley cities like Mohenjo-Daro, and in the workshops of China's Shang dynasty, metallurgists working centuries apart and with no direct contact arrived at nearly identical formulas. A tool blade from one region and a ceremonial axe from another, when analyzed today, often share that magic ratio of roughly 9 parts copper to 1 part tin. This was not a global coincidence, it was the result of a shared process, the scientific method in its earliest, most practical form. Artisans learned through careful observation that altering the recipe changed the metal's soul. A blend with 15% tin yielded a harder, sharper edge, perfect for a sword that needed to hold its line in battle. But that same hardness came with a cost, a greater brittleness. For a craftsman shaping an intricate clasp or a thin-walled vessel, a more forgiving alloy with less tin was essential, allowing the material to be worked without cracking. These were not artistic choices alone, they were engineering decisions based on performance. The transmission of this precise knowledge required a robust system of apprenticeship and trade. A master smith would teach his students not just how to light a furnace, but how to judge the color of the molten metal, how to interpret the sound of a hammer strike on cooled bronze, and the exact proportions that yielded predictable results. This oral and practical tradition formed a living library of material science. When we look at a modern specification sheet for a type of steel or a polymer, with its exact percentages and heat treatment guidelines, we are seeing the direct descendant of those ancient bronze recipes. The core idea remains unchanged. To achieve a desired property, you must control the ingredients with precision. This ancient standardization was the bedrock upon which trust and complexity could grow. A merchant could trade for bronze goods from a distant land with confidence, knowing the alloy's behavior. An army could equip its soldiers with reliable weapons. This hidden protocol, written in the language of chemistry rather than words, was one of humanity's first steps toward a repeatable, scalable technology. It turned inspiration into industry. But the true artistry of bronze was not in its recipe, it was in the shapes it could take. This brings us to the second great technological leap, a process so elegant it feels like magic, the lost wax casting revolution. With a standard alloy, you could make reliable tools, but to capture the curve of a leaf, the delicate features of a face, or the intricate patterns of a myth, you needed a method that could freeze imagination in metal. The lost wax process, known by its French name Sire Perdue, solved this with breathtaking ingenuity. It began not with metal, but with beeswax. An artisan would sculpt their desired object in perfect detail from this soft, pliable material. Every line, every texture, every subtle expression was rendered in wax. This wax original was then coated in a thick layer of clay, creating a mold. Once the clay was hardened by fire, the miracle happened. The mold was heated, and the wax inside melted and drained away through carefully designed channels, leaving behind a perfect hollow cavity, a negative space in the shape of the original sculpture. This is where the name comes from. The wax was lost, sacrificed to create the space for something permanent. Molten bronze was then poured into this empty clay shell, filling every microscopic crevice the wax had occupied. After the metal cooled and solidified, the clay mold was broken away. What remained was a bronze object, an exact metal duplicate of that original wax sculpture. The wax model was destroyed, but its form lived on, immortalized in bronze. This was more than a craft technique, it was a philosophical breakthrough. It allowed for the creation of unique, complex forms that were impossible to carve from solid metal or shape with a hammer. For the first time, human creativity was not limited by the hardness of the material. The artist could work in a soft, forgiving medium to achieve their vision, and then translate that vision into a durable, lasting object. The lost wax process turned thought into tangible reality. It enabled the casting of life-sized statues that conveyed power and grace, of thin-walled vessels adorned with narrative scenes, and of jewelry so fine it seemed woven from metal threads. This technology did not just produce art, it expanded the very language of human expression, giving form to gods, heroes, and the deepest stories of a culture. The molten bronze did not just fill a mold, it filled an idea. The wax model was a temporary vessel for a permanent idea. This ancient technique, known as Sire Perdue or lost wax casting, represents a conceptual leap as profound as the alloy itself. It was a process of planned transformation, where one material was sacrificed so another could take its exact form. An artisan would begin by sculpting their vision in beeswax, a medium soft enough to capture the most delicate details, from the weave of a textile to the curl of a smile. This wax original was then encased in a shell of fine clay, creating a sealed mold. The crucial moment came with fire. As the mold was heated, the wax inside would melt and completely drain away through cleverly designed channels, leaving behind a perfect, hollow cavity. Into this empty space, this negative impression of the original art, molten bronze, was poured. Once cooled, the clay shell was broken away to reveal the metal duplicate. As Dr. Alan Black, a conservator with the British Museum, notes, this technique fundamentally liberated both the artist and the engineer. It allowed for the creation of forms with undercuts, astonishing surface detail, and remarkably thin walls, features simply impossible to achieve by hammering solid metal. This was not merely craft, it was high-concept physics in practice. It required a deep, intuitive understanding of thermal dynamics, knowing how the wax would flow out and the bronze would flow in. It demanded a mastery of material flow to ensure the liquid metal filled every microscopic crevice before solidifying, and it was a brilliant application of negative space, using an absence to create a presence. We see this genius frozen in time, from the intricate gold and silver inlaid scenes on Mycenaean dagger blades to the majestic, ornate ritual vessels of China's Shang dynasty, often used in ceremonies to honor ancestors. These objects were not just possessions, they were manifestations of a technological philosophy that still underpins our world today. The modern process of investment casting, used to create everything from complex jet engine turbine blades to the fine settings for precious gems, is the direct descendant of this ancient method. The materials and precision have changed, but the core principle remains identical: to create a perfect void and fill it with intention. The silent genius of bronze set a precedent, but another material offered a different kind of perfection. From the violent heart of the volcano came obsidian, a glass so sharp it defied the limits of its time. This was not a synthesized alloy, but a gift of geology, born in the superheated womb of the earth and cooled with breathtaking speed. The result was a substance with an edge that could be honed to a monomolecular thinness, far finer than any steel blade produced until the industrial age. To hold an obsidian blade is to hold a frozen moment of cosmic violence, transformed into a tool of astonishing precision. Its story is not one of human recipe, but of human recognition, of seeing potential in nature's most destructive forces. This volcanic glass became the scalpel of the ancient world, a secret weapon for healers and artisans that quietly advanced medicine and art centuries ahead of their time. How could something born from chaos become an instrument of such meticulous control? The answer lies in a fracture, a property known as conchoidal fracturing. When struck with skill, obsidian does not crack randomly like stone. It breaks in smooth, curved arcs, similar to the way thick glass shatters. This predictable fracture allowed a master craftsman to flake off long, thin slivers, each with edges so keen they could split a single cell. Modern surgeons have tested replicas of these ancient blades under electron microscopes and found their cutting edge to be hundreds of times sharper than the finest steel scalpels. This was a technology of the microscopic world, harnessed millennia before the microscope was invented. In the hands of a skilled practitioner, this volcanic glass could perform procedures of incredible delicacy. Evidence from ancient Mesoamerica suggests its use in ceremonial practices, including trepanation, the careful removal of a small piece of skull bone. While the reasons for such procedures are complex and tied to cultural beliefs about illness or spiritual release, the technical requirement was absolute: a cut clean enough to not shatter the surrounding bone, minimizing harm and promoting healing. The obsidian blade, in this context, was not a crude tool but a precise medical instrument. Its legacy challenges our linear view of progress. Here was a material sourced from the earth and shaped by human skill that achieved a level of functional perfection modern technology would not match for thousands of years. It reminds us that innovation is not always about making something new, but sometimes about understanding something ancient on a deeper level. The volcano's destructive gift became, in human hands, a means of careful, deliberate creation. Obsidian's edge was a marvel of nature, but its true power lay in the journeys it inspired. This volcanic glass did not form everywhere, only in the aftermath of specific, violent eruptions where silica-rich lava cooled almost instantly, freezing into a glossy black substance. Such geological events were rare and localized, creating pockets of this precious resource scattered across the globe like isolated islands of potential. In Anatolia, now modern Turkey, the volcanoes of Cappadocia produced vast flows. In the highlands of Mexico, mountains like Cerro de los Navajas, literally Hill of the Knives, were essentially ancient factories for this material. This scarcity did not limit its use, it catalyzed one of humanity's first global systems. Because obsidian was so perfect for specific tasks, and because it could only be found in a few places, people were willing to go to extraordinary lengths to get it. Thus, long before paved roads or written contracts, vast trade networks silently stretched across continents, all tracing back to the flow of this black glass. Archaeologists can trace a blade found hundreds of miles from its source by analyzing its unique chemical fingerprint, a process similar to identifying the origin of a wine by its mineral content. A tool discovered in a village in ancient Mesopotamia might be chemically matched to a volcano in central Turkey, a journey of over 1,000 kilometers. This means someone, or more likely a chain of someones, transported that material across mountains, rivers, and cultural boundaries. These were not simple barter exchanges, but the beginnings of a complex economic web. The trade required knowledge not just of where the obsidian was, but of safe passages, of intermediary communities, and of what those communities valued in return. It fostered communication and created interdependence. A village near the source gained prestige and goods, while a distant community gained access to technology they could not produce locally. This system transformed obsidian from a mere tool into a social catalyst, connecting disparate groups and facilitating the exchange of far more than just material goods. Along these routes, ideas traveled, languages mixed, and technologies were shared. The demand for a sharper blade inadvertently wove the first threads of a connected world, proving that sometimes the most profound innovation is not in the object itself, but in the human systems we build to obtain it. The obsidian blade's perfection was not a gift easily claimed. It demanded a third technological leap, the art of pressure flaking, a skill so subtle it bordered on telepathy between the craftsman and the stone. This was not about brute force. You could not simply strike obsidian with a hammer and expect a surgical edge. Instead, the artisan used a precise, controlled push. They would take a core of raw glass and, using a tool made of antler or hard wood, apply steady pressure to a specific point along its edge. With a faint, almost musical ping, a long, thin flake would shear away, leaving behind a scar of impossible smoothness. This was subtractive manufacturing at its most elegant. The craftsman was not adding material, but carefully removing everything that was not the blade. Each controlled fracture refined the shape, thinning the piece, straightening its edge, and preparing it for the next, even finer removal. The process was a conversation. The flint knapper had to read the material's internal structure, its hidden flaws and grain, applying just enough force to guide the fracture without shattering the entire piece. It was a mastery of fracture mechanics achieved through touch and intuition, a knowledge written in the muscles and nerves of the hand. We can see the legacy of this ancient skill in the breathtaking mosaics of the Aztec Empire, where thousands of these razor-sharp flakes were set into wooden frames to create shimmering, textured sculptures of gods and serpents. Each tiny piece, no larger than a fingernail, was a testament to this controlled pressure, shaped to interlock perfectly with its neighbors, but the principle extends far beyond art. In a modern cleanroom, technicians use focused ion beams to etch circuits onto silicon wafers, removing atoms with pinpoint accuracy to create microchips. While the scale and tools are galaxies apart, the underlying philosophy is the same: the deliberate, controlled removal of material to reveal a complex, functional form within. The obsidian worker, patiently pressing a flake from volcanic glass, was engaging in the same fundamental act of precision engineering. Their technology was not in the tool they used, but in the calibrated intention behind every movement, a silent algorithm of force and angle that transformed chaotic nature into exquisite order. The obsidian itself was only half the story. To unlock its potential, ancient artisans developed a technique of breathtaking subtlety, a dialogue with the stone known as pressure flaking. Forget the image of hammering rock against rock. This was a quieter, more intimate art. The craftsman would brace a core of glossy black glass, then take a tool of antler or seasoned hardwood, placing its tip against a precisely chosen point on the stone's edge. Instead of a strike, they applied a steady, rolling inward pressure, leaning their body weight into the push. With a soft, crystalline sound, a long, ribbon-like flake would peel away, leaving behind a surface as smooth as still water. This method granted a sculptor's control over the fracturing glass, allowing for the creation of blades so thin they were almost translucent and points so symmetrical they seem machined. Each successful flake removed was a triumph of applied physics, a manipulation of the material's internal tensions guided solely by touch and intuition. As experimental archaeologist Dr. Ella Torres explains through replication studies, creating the obsidian blades for an Aztec macuahuitl, a wooden sword lined with these lethal glass shards, demanded far more than strength. It required a deep, tactile understanding of fracture mechanics, a knowledge passed down through a lifetime of apprenticeship. The master flintknapper knew exactly how much pressure to apply, at what angle, and where, to guide the crack exactly where they wanted it to go. This hands-on mastery represents a peak of ancient technology, a skill set so refined that modern material scientists now study these ancient techniques. They look to this old knowledge to better understand how fractures propagate in advanced ceramics and synthetic glass, seeking clues for making our own brittle materials tougher and more predictable. The artisan patiently pressing a flake from volcanic glass was, in essence, conducting a primitive but profoundly accurate experiment in material science, their hands serving as both laboratory and measuring instrument. This intimate conversation between human and stone yielded an edge that defined an era, proving that the most advanced technology is sometimes not a tool you build, but a skill you embody. This monomolecular edge found its most profound purpose not on the battlefield, but in the healer's hand. The same volcanic glass that could shatter bone could also, with breathtaking precision, part living tissue with minimal trauma. In the ancient Americas, obsidian became a surgical instrument of choice. Its scalpel-sharp flakes allowed for incisions so clean they promoted faster healing with less scarring than the crude metal tools available at the time. Modern experiments confirm this, showing that obsidian blades produce a smoother cut under the microscope than even the finest steel, causing less cellular damage along the wound edge. This was advanced medical technology, born from a deep empirical understanding of the material's unique properties. But to view this only through a modern medical lens is to miss half of its significance. In the worldview of many ancient cultures, the line between the physical and the spiritual was not a barrier, but a permeable membrane. A physical illness was often seen as having a spiritual component, a disruption or imbalance that needed addressing. Therefore, a tool used for healing was, by its very nature, also a spiritual instrument. The obsidian blade's origin from the sacred, volatile heart of the volcano lent it a powerful symbolism. It was a substance born of earth and fire, capable of opening a path not just through flesh but between worlds. In practices like trepanation, the careful removal of a small disc of skull bone, the objective was likely multifaceted. While researchers suggest it may have been intended to relieve pressure from head injuries, the act also carried profound ritual meaning for many cultures, possibly seen as a way to release spiritual pressure or allow closer connection to the divine. The surgeon priest wielding the obsidian blade was thus performing a dual act, attending to the body while engaging in a ceremonial practice for the individual's overall well-being. The tool itself was neutral, a vessel of pure potential. Its application, whether for crafting a ceremonial mask, performing a medical procedure, or creating an offering, was dictated by the intention behind it. This duality is obsidian's ultimate technological legacy. It demonstrates that for our ancestors, innovation was never just about functionality. The most advanced tool was one that served both the tangible and the intangible needs of the community, bridging the gap between the physical problem and the human story surrounding it. The cold, sharp glass became warm with meaning, a conduit for care that was holistic in the truest sense. A polished obsidian mirror does not reflect your face, it reveals a different world entirely. This duality is the core of its legacy, a single material serving two seemingly opposite human needs, the empirical and the ethereal. In the highlands of ancient Anatolia, now Turkey, archaeologists have unearthed obsidian blades at sites like Çatalhöyük, one of the world's earliest large settlements. Under the microscope, the cut marks on human bones found there tell a silent, stunning story. They are not jagged or rough, but clean and precise, showing evidence of careful scraping and cutting that likely correspond to early surgical procedures. This suggests a practical, hands-on knowledge of anatomy and a desire to intervene directly upon the body, to mend or perhaps to understand. The tool was an extension of a healer's focused intention, grounded in the physical reality of flesh and bone. Now, journey across the globe and centuries forward to the great civilizations of Mesoamerica. Here, artisans took the same volcanic glass and transformed it through endless polishing into mirrors with surfaces so flawless they became jet-black pools of darkness. These were not for vanity. To cultures like the Maya and the Aztecs, these mirrors were Tezcatl, sacred instruments of divination. They were believed to be portals, smoky windows into the spirit world, used by priests and rulers to scry for visions, communicate with ancestors, or foresee events. The same substance that could part tissue with cellular precision was also thought to part the veil between realms. This is not a contradiction in the ancient mind, but a harmony. It reveals a world where technology was never a sterile, standalone tool. Mastery over a material like obsidian was a form of power, and that power could be applied to any domain of existence, from the very concrete task of healing a body to the profound, symbolic act of seeking spiritual insight. The craftsman who shaped the scalpel and the priest who gazed into the mirror were both engaging with the same fundamental truth, that humanity could harness the secrets of the earth to interface with the mysteries of life itself. This holistic approach challenges our modern compartmentalization of science, medicine, art, and religion. For our ancestors, the sharpest blade was also a key, capable of unlocking both the body and the cosmos. If obsidian was the scalpel, then limestone was the canvas. This humble sedimentary rock, formed from the compressed skeletons of ancient sea life, became the literal bedrock upon which civilizations built their most enduring statements. It is soft enough to be carved with copper tools when first quarried, yet hardens upon exposure to air, gaining a durability that can defy millennia. But its true technological legacy is not just in its permanence, it is in the scale of ambition it permitted and the silent engineering required to wield it. To move from quarry to temple, these stones had to conquer gravity and distance, a challenge that sparked some of history's most ingenious feats of logistics. The story of limestone is a story of mass mobilization, of levers, ramps, and communal will transforming a mountain into a message. What does it take to convince a 100-ton block of stone to float across the desert? The ancient Egyptians provided an answer that still echoes with quiet brilliance. For the Great Pyramid of Giza, the sheer volume of limestone required was staggering, over 2 million individual blocks. But the quarries were not at the construction site, they were across the Nile River and upstream. The solution was not to fight the landscape, but to collaborate with it. During the annual inundation, when the Nile's floodwaters spread across the land, engineers dug canals directly from the river to the base of the Giza Plateau. They then loaded the massive stones onto specially built, flat-bottomed barges. When the floods receded, they were left with a network of water highways that had carried the mountain to the building site. This was seasonal engineering on a grand scale, using a natural, predictable cycle as a machine. Once ashore, the journey was not over. The stones then had to be dragged up ramps, likely spiraling around the growing structure. This is where the humble lever and the lubricated sled came into play. Experiments have shown that a team of workers could move a massive block on a wooden sled by constantly placing and repositioning wooden rails in front of it. a technique requiring coordination more than brute force. Pouring water or a slurry of wet clay in front of the sled dramatically reduced friction, making the impossible merely difficult. This was physics in action, a distributed system where human intelligence amplified muscle. The pyramid was not just a tomb, it was a testament to a society that could organize time, labor, and natural forces with the precision of a symphony conductor. Every block placed was a victory over inertia, a lesson in turning collective effort into a permanent monument. That soft, workable stone was also humanity's first hard drive. Limestone's true revolution lay not just in what it could hold up, but in what it could hold within. Its surface became a page. When freshly quarried, its surface is soft enough for a scribe's stylus or a carver's chisel to leave a clear, deep mark. Then, as it cures in the open air, it petrifies that mark, locking the message into a matrix that can endure for ages. This combination of initial malleability and ultimate permanence made it the perfect medium for a civilization's most important thoughts. From the detailed legal codes of Hammurabi, carved into a towering basalt stele, to the intricate accounting records of Sumerian city-states pressed into countless clay and stone tablets, limestone and its cousins provided the physical substrate for abstract ideas. It turned spoken words into visible, lasting objects. As epigrapher Dr. Samuel Chen observes, choosing limestone for inscriptions was a deliberate technological choice for permanence. It was a way to converse with the future, to etch cultural memory into the very bones of the earth. Think of the Rosetta Stone, the fragment of granodiorite that gave us the key to Egyptian hieroglyphs. Its message, a mundane priestly decree, was insignificant compared to the technological function it served millennia later, a linguistic bridge carved in stone. Or consider the massive limestone stelae of the ancient Maya, erected in city plazas. They were not mere monuments, they were public archives. They recorded the ascensions of kings, the dates of celestial events, and complex calendrical cycles, ensuring that a ruler's legacy and a society's understanding of time would outlive the dynasty itself. This transforms limestone from a simple construction material into an early form of data storage. The quarry was the server farm, the carver was the programmer, and the finished steel was a read-only file of immense cultural importance, designed to be accessed by generations yet unborn. In a world before paper, before digital clouds, this was how a civilization backed up its soul, choosing the slow, sure memory of geology over the fragile recall of human tradition. That silent memory of stone leads us to the fourth great technological leap, a hidden language of numbers and force. Before the written theorem, before the formal equation, ancient builders were fluent in a practical mathematics of mass and equilibrium. They were solving complex engineering problems on a colossal scale, using principles we still rely upon today. This was megalithic mathematics, the invisible framework that allowed humanity to defy gravity itself. Consider the simple yet profound act of raising a massive lintel stone onto two upright pillars, like those at Stonehenge or in the doorways of Mycenae. The builders were not just stacking rocks, they were intuitively applying the concept of the post and lintel, a fundamental principle of architecture that manages compressive stress. They understood that the upright posts could bear immense downward weight, and that the horizontal lintel could span an open space, creating a doorway or a window. To get that multi-ton lintel into position, they likely employed an early form of the lever and fulcrum, perhaps using timber cribbing to raise it incrementally, a process requiring precise calculation of balance points and pivot locations. Or consider the corbelled arch found in structures like the treasury of Atreus in Greece. Here, stones are layered in such a way that each course projects slightly inward over the one below, until the walls meet at the top. This technique creates a stable, domed space without needing a true arch with a keystone. It is a brilliant application of incremental overhang, where each stone's weight is carefully counterbalanced by the one opposing it. The builders were masters of statics, arranging mass to achieve stability through geometry. They worked with a tactile understanding of center of gravity, load distribution, and friction. They knew that a stone dragged on a sled required a different angle of pull on level ground than on an incline, a practical application of vectors. Their construction sites were open-air classrooms for physics, where every successful placement was a solved equation written in limestone and granite. This was not abstract math, but mathematics embodied, a knowledge held in the hands, eyes, and communal effort of the builders. Their legacy is the enduring proof that some of our most advanced understanding is first learned not on parchment, but through the patient, physical dialogue with weight and balance. The scale of these projects still defies belief. To stand at the base of the Great Pyramid is to confront a mountain made by human hands, a geometric form assembled from 2.3 million blocks of limestone and granite, each one averaging 2.5 tons. This was not a haphazard pile. It was a feat of precision logistics that would challenge a modern construction firm. The true engineering marvel often lies invisible to us in the journey of each block from quarry to final resting place. Quarries for the fine white casing stones were located across the Nile River. The solution was a masterpiece of seasonal adaptation. During the annual flood, workers dug canals directly to the base of the Giza Plateau. Massive stones were loaded onto barges and floated right to the construction site, turning a destructive natural event into a delivery system. Once on land, the real work began. How do you move a 70-ton granite beam for a king's chamber? The evidence points to wooden sledges gliding over tracks of lubricated limestone. Experiments have shown that wetting the path ahead of a sledge can reduce the pulling force required by over 50%. Teams of workers, coordinated by rhythm and command, could then walk these behemoths up earthen ramps that spiraled around the growing structure. This was physics made communal, a distributed system where intelligence triumphed over mass. The silence between the stones speaks volumes. At sites like the Inca walls of Sacsayhuaman or the inner chambers of the Great Pyramid, you find masonry fitted so tightly that a razor blade cannot slip between the joints. This perfection, achieved without mortar, implies a technological ecosystem far beyond brute strength. It required advanced surveying to maintain perfect level and alignment across acres of construction. It demanded a standardized unit of measurement, a consistent cubit or foot, used by every team on site to ensure every block was interchangeable. Most profoundly, it points to a shared, sophisticated plan, an ancient blueprint held in the mind of a master architect and translated into reality by a society capable of specialized roles. Quarrymen understood grain and fracture points. Transport crews mastered leverage and friction. Setters and finishers possessed the eye and hand of master craftsmen. This was early project management on a civilization-defining scale, a symphony of coordinated labor where the conductor was a geometric vision. The structure itself was the proof of concept, a testament to a society that could organize time, knowledge, and thousands of people toward a single, enduring goal. Their legacy is not just the stone, but the invisible architecture of cooperation that made it possible. A finished temple is not a silent place. Within certain ancient stone chambers, a whisper can transform. Speak softly in the heart of a pyramid's burial vault, or inside a Neolithic passage tomb like Newgrange in Ireland, and your voice does not fade. It lingers, swelling into a deep, resonant hum that seems to come from the stone itself. This is not an architectural accident. It is a deliberate feature, an acoustic engineering so precise it feels like magic. These spaces were designed with specific sonic properties, turning inert limestone and granite into instruments of profound experience. The builders shaped not just sight but sound. They understood that the geometry of a room, its dimensions, the angles of its walls, the smoothness of its surfaces, could control how breath and vibration moved through the air. In a perfectly resonant chamber, certain low frequencies are amplified. A chant, a drum beat, or even the rhythmic clap of hands could generate a powerful, enveloping drone, a physical sensation that vibrates in the chest as much as it is heard by the ears. This sonic environment would have utterly transformed ceremonies held within. The boundary between the individual and the group could blur as the shared sound became a tangible, unifying force. The very stones seemed to participate, answering human voice with their own deep, ancient song. Researchers using modern acoustic mapping have confirmed these effects in sites across the world. The Mayan temple of Kukulkan at Chichen Itza produces a chirping echo that mimics the call of the sacred Quetzal bird when you clap at its base. The hypogeum of Hal Saflieni in Malta, a labyrinthine underground sanctuary carved from solid limestone, contains a chamber known as the Oracle Room, where a deep male voice spoken into a niche creates a resonance that seems to fill the entire complex. This was not decorative, it was functional technology. By sculpting sound, the architects were sculpting consciousness, using physics to engineer a specific state of awe, focus, or communal connection. The chamber became more than a room. It was a resonant vessel for ritual, proving that the most advanced ancient technology often worked on the senses in ways we are only beginning to measure. That resonant hum within the stone is a clue to a deeper layer of knowledge. Archaeoacoustics, the study of sound in ancient spaces, reveals that our ancestors were not just building for the eye, but for the ear. Take the great passage tomb of Newgrange in Ireland, its facade glittering with white quartz and granite cobbles, or the Hal Saflieni hypogeum on Malta, an entire sanctuary carved 3 stories down into the living limestone. Within these structures, specific chambers are not acoustically neutral. They are finely tuned instruments. A low chant or a steady drumbeat in these spaces does not simply echo, it transforms. The geometry of the room, the texture of the walls, and the very dimensions of the space can amplify certain frequencies, creating a pervasive, physical drone that vibrates in the chest and seems to emanate from the earth itself. This can produce auditory illusions where sound appears to come from everywhere and nowhere, or even induce a sense of weightlessness or focus that some researchers associate with meditative states. The work of researchers like Professor Robert John of Princeton University lends weight to the idea that this was more than coincidence. He suggested that the architectural manipulation of sound could have been a deliberate technological application used to amplify ritual chanting, create auditory illusions, or facilitate meditative or shamanic practices. This implies an empirical, if intuitive, grasp of sound wave behavior, how it reflects, interferes, and resonates within a confined space. They were practicing a form of acoustic engineering millennia before the science had a name. By shaping stone to shape sound, these ancient builders were engineering experience itself, using the physics of vibration to deepen ceremony, unify a group, or bridge the perceived gap between the earthly and the spiritual. The chamber became a tool for transformation, proving their technology worked on the most intimate frontier, the human mind and spirit. The true genius of these materials emerges when they are no longer alone. Bronze, obsidian, and limestone did not exist in separate technological silos. Their most profound legacy is found in the moments they converged, creating a synergy far greater than the sum of their parts. This intermaterial synergy is where ancient engineering truly sang. Consider the Egyptian pyramid not as a pile of stone, but as a composite system. The massive limestone blocks formed the enduring body, but the precision work required to fit them relied on copper and bronze tools for cutting and shaping. To dress the fine outer casing stones to a mirror-smooth finish, artisans likely used abrasive pastes made from crushed quartz or even emery, materials harder than the metal tools themselves. Here, a softer metal was used to work a harder stone, with an even harder abrasive acting as the intermediary. This is a three-material technological chain, each playing a specific role in the process. Or look to the warrior of the ancient Americas. A wooden macuahuatl sword becomes a devastating weapon not through the wood, but through the rows of obsidian blades meticulously fitted into slots along its edges. The wood provides the structure and leverage, the sharp volcanic glass provides the cutting edge, and the binding, perhaps made from plant fibers or leather, holds the system together under the stress of impact. This is composite material science in action, combining the properties of different substances to achieve a performance none could manage alone. Even in medicine, we see this convergence. A surgeon priest might use a bronze lancet for a broader incision, but reach for an obsidian flake for the most delicate work around sensitive areas, selecting the right material for the specific task from a toolkit of options. This conscious selection and combination represent a sophisticated understanding of material properties. It moves from simply using what is at hand to designing a system. The legacy is not in the bronze sword, the obsidian blade, or the limestone wall by itself. The legacy is in the mind that could see how these pieces fit together, how the hardness of one could solve the weakness of another, and how their union could create something entirely new. This ancient principle of synergy is the direct ancestor of every modern composite, from fiberglass to carbon fiber, where materials are layered and combined to create substances that can fly, dive, and endure in ways their individual components never could. The silent conversation between bronze, glass, and stone was humanity's first step toward designing the very fabric of reality. A bronze chisel is more than a tool, it is a translator. It speaks the language of fire and alloy, but its purpose is to converse with stone. This simple metal wedge, born from the alchemical furnace, became the indispensable hand that shaped civilization's bones. Without the hardness and durability of bronze, the grand-scale quarrying of limestone would have remained a dream. Copper alone was too soft, its edge blunting quickly against the stubborn rock. But the tin-bronze alloy provided a resilient bite, allowing teams to pound chisels along natural fracture lines, prying multi-ton blocks from the living bedrock. Once quarried, that same chisel, in the hands of a master carver, became a delicate pencil. It translated architectural plans into reality, dressing rough blocks into precise, interlocking shapes, and later, it etched history and belief into temple walls with intricate hieroglyphs and reliefs. The chisel was the critical interface between two technological worlds, the synthesized metal and the sedimentary earth. This synergy extended into even finer work through the bronze-tipped drill. To bore a hole through granite or to hollow out a stone vessel, brute force was useless. The solution was a clever marriage of materials. A bronze rod, rotated by a bow or a pump drill, would be used not to cut the stone directly, but as a delivery system. The craftsman would feed an abrasive paste of crushed quartz or emery sand into the contact point. The bronze tool, softer than the stone, would actually wear away, but in doing so, it continuously embedded fresh, harder abrasive particles into the work surface. The real cutting was done by the sand, with the bronze acting as the carrier and the power transmitter. This was a composite tool in action, combining the torsional strength of metal with the relentless hardness of natural minerals to solve a problem neither could tackle alone. On the other side of the material spectrum, obsidian played its own crucial supporting role. While bronze handled the macro-scale work of moving and shaping stone, obsidian's monomolecular edge attended to the micro-scale. A master craftsman might use a razor-sharp obsidian flake for the final, meticulous detailing on the wooden handle of a bronze adze, or for cutting and fitting the leather straps that secured a stone block to its sledge. In creating architectural fittings or ceremonial objects, obsidian could cleanly trim delicate inlays of shell or turquoise, or scrape a wooden beam to a perfect fit. Its unparalleled sharpness made it the perfect finishing tool in a technological ecosystem that relied on multiple materials working in concert. This interconnected use reveals something profound, an ancient holistic technological network. Advancements in metallurgy did not happen in a vacuum. They directly enabled breakthroughs in masonry. The ability to shape stone on a monumental scale, in turn, created a demand for more durable metal tools, fueling further innovation in alloy recipes and forging techniques. The existence of fine obsidian blades encouraged craftsmanship in wood and leather, which were essential components for the tools and machines used in both metalworking and construction. It was a virtuous feedback loop, a silent conversation between the quarry, the forge, and the workshop. A better chisel meant more precise stonework, which allowed for grander architectural designs, which then required even more sophisticated tools to maintain and decorate. This was not a collection of separate inventions, but a living, evolving ecosystem of innovation. The true landscape of ancient technology is found in these handshakes between materials, where the strength of one perfectly compensated for the limitation of another, weaving a resilient tapestry of human ingenuity. That silent conversation between materials forged more than objects. It forged a new way of thinking. The deepest legacy of bronze, obsidian, and limestone is not in the artifacts left behind, but in the cognitive architecture they helped build within us. Working with these substances trained the human mind in two fundamental skills: pattern recognition and abstract thought. Consider the bronze smith at their crucible. They did not see just copper and tin, they saw a relationship. Through endless trials, they learned to recognize the visual pattern of the perfect melt, the specific color and flow that signaled the ideal alloy. They had to hold in their mind an abstract concept, the recipe, and then manifest it in the physical world. This is a leap from observation to intervention. Similarly, the obsidian flintknapper did not see a random chunk of glass. They learned to read the stone's internal geometry, its hidden fault lines and conchoidal fracture patterns, predicting how a single point of pressure would travel through the entire core. They were seeing the future shape within the raw material, a profound act of mental projection. And the limestone architect, they looked at a rugged cliff face and saw within it the smooth planes of a future wall, a pyramid, or a statue. They had to translate a three-dimensional vision in their mind into a sequence of physical actions performed on an inert block. This constant practice of seeing the potential within the raw, of manipulating the tangible to achieve an intangible idea, fundamentally rewired our cognitive capabilities. It moved us from reactive creatures to proactive designers. We stopped just responding to the environment and started imprinting our imagination upon it. The true monument was not the finished temple, but the new kind of mind that could conceive of it. That evolved mind did not just build things, it built new ways of thinking. The consistent crafting of bronze, obsidian, and limestone was a rigorous training ground for the human brain, forging cognitive skills as durable as the materials themselves. Each substance presented a unique mental challenge. For the bronze smith, success depended on pattern recognition. They had to observe that a specific color in the molten metal, a particular sound when struck, consistently correlated with a blade that would not bend or a tool that would not shatter. This was not magic, it was early data analysis connecting cause and effect through careful, repeated observation. The artisan was learning to read the subtle language of material behavior, a skill that is the very foundation of the scientific method. Then there was the obsidian worker holding a rough, opaque core of volcanic glass. Before a single flake was removed, they had to see the finished blade within it. This required intense three-dimensional visualization and planning. They had to mentally map a sequence of precise pressures, each one shaping the stone toward that invisible final form, anticipating how each fracture would alter the geometry of what remained. This is the cognitive ancestor of modern engineering simulation, running a complex process in the mind before executing it in reality. And for the architects of megaliths, the challenge was one of sheer abstract thought. They had to conceive of a structure like Stonehenge or the Great Pyramid in its entirety, its scale, its alignment, its stability, long before a single stone was set. They worked from a vision that could not be seen or touched until perhaps decades of labor were complete. This demanded advanced spatial reasoning, logistical foresight, and the ability to hold a complex, multi-step plan across time and a vast workforce. As cognitive archaeologist Dr. Fiona Green explains, these material engagements were cognitive gymnasiums. They trained the brain in sequential logic, cause and effect reasoning, and spatial manipulation, skills that are the bedrock of modern science and engineering. The true technological legacy, therefore, transcends the physical object. It resides in the evolved human capacity to think in terms of systems, processes, and invisible relationships. When we solve a modern problem using logic or visualize a complex design, we are using cognitive tools sharpened by ancient hands working bronze, glass, and stone. This cognitive evolution found its physical expression in a simple yet revolutionary concept, the specialized toolkit. The fifth great technological leap was not a single invention, but an organizational principle, a way of thinking about problems that divided them into parts and assigned the perfect tool for each task. It marked the end of the universal implement and the dawn of precision. No longer would a single stone hand axe try to do everything from chopping wood to scraping hide. Now a craftsman approaching a block of limestone would have a kit, a heavy bronze pick for rough quarrying, a finer chisel for dressing the stone's face, a delicate obsidian flake for incising decorative lines, and a sandstone block for the final polish. Each tool was an answer to a specific question of force, friction, and finish. This was the birth of applied ergonomics and workflow optimization. It recognized that material transformation is a process, a sequence of stages requiring different kinds of intervention. We see this beautifully preserved in the tomb paintings of ancient Egypt, where artisans are depicted not with one tool, but with an array, each held ready for a specific moment in the creation of a statue or a coffin. The toolkit was a physical manifestation of sequenced thought. It required foresight to prepare, knowledge to select, and skill to wield. This principle scaled from the individual artisan's belt to the entire worksite. The pyramid project itself was a macro toolkit with specialized crews for quarrying, transport, ramping, setting, and finishing, each a tool in the grand logistical machine. The development of specialized toolkits represents a fundamental shift from reacting to a material with whatever was at hand to proactively designing a system of interaction. It is the moment technology became modular, adaptable, and infinitely scalable. The legacy of this leap is in every modern workshop, surgery, and laboratory, where the specificity of the instrument is the direct measure of our understanding. A specialized toolkit is a silent argument for expertise. The sheer variety of implements found in ancient workshops tells a clear story, one of purpose over convenience. We do not discover a generic bronze tool, but a carefully curated collection, each piece answering a specific need. For working stone, a smith would cast a stout, flat chisels designed to withstand hammer blows against limestone. For shaping wood, they needed narrow gouges that could scoop out precise channels. For clearing land or preparing timber, heavy axes with a specific bevel angle were essential. And for the finest work on leather or textiles, impossibly slender bronze needles, sometimes with eyes smaller than a modern sewing needle, were crafted. Each of these required not just a different shape, but often a subtly different alloy. The axe needed a harder, more impact-resistant bronze, while the needle required a more malleable mix that could be drawn out thin without breaking. This was not happenstance, it was a material science tailored to function. The same precision governed the Obsidian worker's kit. It was a complete production system contained in a pouch or basket. It held the raw cores of volcanic glass, the preforms partially shaped into rough blanks, the antler tines used for the final, delicate pressure flaking, and the heavier stone billets for the initial percussion work to break the core down. Each tool had a single role in the multi-stage ballet of creating a blade. You would not use the fine pressure flaker to strike the core, just as you would not use the rough billet to put the final edge on a scalpel. This toolkit represents a sequenced thought process made physical, a step-by-step workflow that ensured consistency and quality from raw stone to finished artifact. For the limestone mason, the toolkit scaled up in both size and complexity. The work began with heavy pounders, fist-sized stones of dolerite, a rock harder than limestone, used to bash along natural fracture lines in the quarry. Then came the copper saws, which were less like cutting tools and more like guided abrasion systems. These thin sheets of metal, pulled back and forth by teams of workers, did not cut the stone so much as grind it, with sand or crushed quartz constantly fed into the groove to act as the true abrasive. Finally, for the finishing touch, there were polishing stones of increasingly fine grit, often sandstone or emery, rubbed for hours to bring the limestone surface to a reflective sheen. Each tool addressed a specific phase of the transformation, from brute separation to refined perfection. This move from a generalist single tool to an expert's diversified kit marks a profound social and economic shift. It signals the birth of specialized trades. A person was no longer just a craftsperson. They became a woodworker specializing in bronze gouges, or a mason master of the copper saw and abrasive. This division of labor allowed for deep skill accumulation. An artisan could spend a lifetime perfecting the use of one set of tools on one material, achieving a level of quality and efficiency impossible for a jack of all trades. It turned technology from a universal survival skill into a profession, a dedicated pursuit that formed the economic backbone of towns and cities. The specialized toolkit, therefore, is more than a collection of objects. It is the physical evidence of a society organizing itself for excellence, investing in deep knowledge, and building a world where complexity could thrive. The specialized toolkit was a local masterpiece, but its components often came from distant lands. This reveals the sixth great technological leap, the sprawling trade networks that acted as the silent circulatory system of the ancient world. These were not simple paths for merchants, but the vital veins of technological exchange, carrying not just goods, but the very seeds of innovation across mountains, deserts, and seas. A bronze smith in Mesopotamia could not work without tin, yet tin mines were exceedingly rare, found only in places like distant Afghanistan or Cornwall in Britain. The existence of bronze across entire continents is proof of a web of connections so resilient it could move a critical ingredient across thousands of miles. Similarly, the glossy black obsidian used in Anatolia or Mexico traveled far from its volcanic sources, passed from hand to hand through a chain of intermediaries. These networks transformed scarcity into opportunity. A village sitting atop an obsidian flow did not just have superior tools, it had a commodity that could be traded for seashells from the coast, rare pigments from distant mountains, or exotic woods from the rainforest. This exchange was about more than wealth, it was about knowledge. When a trader delivered a load of tin ore, they were also delivering a question: how do you use this? The receiving culture had to learn the smelting techniques, the alloy ratios, and the forging methods, often adapting them to their own local fuels and customs. In this way, technology was not invented in isolation, but cross-pollinated along these invisible routes. A decorative motif developed for a bronze dagger in one region might inspire the carving on a stone seal in another. The standardized weight system used to measure silver in trade might later be adopted by architects to standardize brick sizes. The flow of materials created a flow of ideas, making these networks the ancient equivalent of the internet, a slow but profound connective tissue that allowed human ingenuity to compound. The desert caravans and coastal dhows were carrying the future, one ingot, one core of glass at a time. The map of these materials reveals an ancient world already deeply connected. Tin, the essential partner to copper in creating bronze, was astonishingly rare in nature. Major deposits existed only in a handful of places like Cornwall in Britain, the mountains of Afghanistan, and parts of Anatolia. Yet bronze artifacts appear everywhere from Scandinavia to the Indus Valley. This means that for centuries, perhaps millennia, a tin gold mined in Central Asia could end up in a foundry beside the Mediterranean, a journey of over 3,000 miles. This was not occasional barter, but a sustained, organized flow. Similarly, the chemical signature of obsidian from a single volcano in central Turkey has been identified in tools excavated as far away as the southern Levant. In the Americas, the distinctive green obsidian from Pachuca in Mexico traveled along established routes to become prized ceremonial objects in Maya cities hundreds of miles to the south. Even limestone, seemingly common, was often specifically sourced. The flawless white casing stones for Egypt's pyramids came from quarries at Tura, across the Nile, while the Romans famously prized a specific honey-colored limestone from quarries in Syria for their grandest temples. These were deliberate choices, not accidents of geography. The movement of these materials was sustained by sophisticated and resilient systems, both maritime and overland. Merchant ships plied the coasts of the Mediterranean and the Indian Ocean, their hulls laden with ingots and raw stone. Caravans wound through mountain passes and across deserts, following oasis to oasis, guided by generations of accumulated knowledge about seasons, safe passages, and reliable trading partners. These networks formed the skeletal framework of early globalization. They functioned as the Internet of Antiquity, a physical web for transmitting information. But instead of data packets, they carried something equally transformative, tangible pieces of innovation. A shipment of tin was never just metal. It came with the implied knowledge of how to use it, the smelting techniques, the ideal alloy ratios. Alongside the obsidian cores traveled the skill of pressure flaking. With the limestone blocks came the architectural principles for building with them. This constant flow meant that technological styles were in constant dialogue. A beautifully crafted bronze sword from the Aegean, with its intricate hilt and leaf-shaped blade, might be traded north. In Central Europe, a local smith would examine this foreign object, appreciate its balance and craftsmanship, and then adapt its elements into their own work, creating a hybrid design that blended local tradition with distant inspiration. This demonstrates a powerful truth that the most vibrant periods of technological innovation were rarely born in isolation. They were the product of cultural connection, the spark that flies when one world's solution meets another's problem. The trade routes were conduits for curiosity, carrying not just commodities but the very questions and answers that propelled humanity forward. These trade routes carried more than commodities, they carried meaning. The materials that traveled such vast distances, bronze ingots, obsidian cores, blocks of prized limestone, were never seen as mere raw supplies. They were imbued with significance, their journey from source to sacred site transforming them into objects of power. This is where we encounter a profound shift in the story of these materials, the ritualization of technology. The process of creating with bronze, obsidian, or stone was often inseparable from the ceremonial acts that gave a society its identity and connection to the cosmos. The forge, the flint knapper's station, and the quarry were not just workshops, they were stages for a deeper performance. Take the casting of a bronze ceremonial vessel in ancient China, perhaps a massive ding used to make offerings to ancestors. The process was a meticulously choreographed ritual. The selection of the ores, the timing of the smelt to coincide with auspicious celestial events, the inscribing of the mold with symbolic patterns, all of these steps were governed by tradition and belief. The molten bronze poured into the mold was not just becoming a container, it was becoming a conduit. The finished vessel, adorned with touty masks and dragon motifs, was a technological masterpiece, but its primary function was to mediate between the living and the spiritual realm. Its physical perfection was proof of ritual correctness, its very existence a testament to a harmonious relationship with unseen forces. The technology served the ceremony, and the ceremony sanctified the technology. We see this fusion even more vividly in the world of obsidian. For the Aztecs, the volcanic glass was not just a practical material, it was the blood of the earth, a sacred substance born from the conflict of gods. The act of pressure flaking a blade was therefore a sacred act, a participation in that primordial drama. A mirror polished from obsidian, known as a Tezcatl, was a portal. It did not show a reflection of this world, but a smoky glimpse into the world of spirits, used by priests for divination. Here, the ultimate expression of the material's technological potential, a flawlessly smooth surface, was dedicated entirely to a spiritual purpose. The sharpest blade and the darkest mirror were two sides of the same sacred coin, both products of a skill set that was as much about ritual knowledge as it was about manual dexterity. Perhaps the most stunning example lies in the megalithic landscapes of places like Stonehenge. The transportation and erection of those massive sarsen stones was a colossal engineering feat, a triumph of logistics, leverage, and communal labor. But to view it only as an engineering project is to miss its heart. The entire endeavor was likely a grand ritual in itself. The journey of the stones from distant quarries may have reenacted a mythological voyage. The alignment of the monument with the solstice sun was not an accidental byproduct of construction. It was the central design specification. The technology of moving and raising stone was employed to create a permanent machine for tracking time, for marking the sacred cycles of the year, and for gathering the community in moments of celestial significance. The construction was the ceremony, a decades-long act of worship written in limestone and earth. This ritualization solves a fascinating puzzle. How did these ancient societies muster the sustained will to undertake projects that span generations? The answer often lies in this fusion. When technology is woven into the fabric of belief, it ceases to be a mundane task. Quarrying a stone for the king's pyramid is not just hard labor, it is a step toward ensuring his eternal journey and the continued order of the universe. Forging a bronze sword for a hero is not just metallurgy, it is infusing the metal with the blessings of the gods for victory. The ritual provided the why, the profound motivation that transformed exhausting labor into purposeful, even sacred, action. It connected the immediate, physical effort of the individual to a grand, timeless narrative for the community. In this light, the most enduring monuments are not just testaments to what these people could build, but to what they believed was worth building for. The true innovation was recognizing that the mind shaping the material also needed a story to give that shape meaning. The ritual was the blueprint. Every strike of the hammer, every pour of molten metal, was guided by an unseen script that connected the workshop to the heavens. When a bronze smith prepared their crucible, the act was rarely a solitary, technical one. Before lighting the furnace, offerings might be made to the deities of earth, who provided the ore, and to the gods of fire, who would transform it. Chants or specific songs could accompany the bellows, their rhythm ensuring the fire burned at the right temperament. This was not superstition, but a sophisticated framework. In a world without textbooks on metallurgy, the ritual encoded the correct procedure, the precise timing, and the respectful handling of powerful, dangerous forces into a memorable, repeatable ceremony. It turned a chemical reaction into a collaborative act with the divine, ensuring that every step from ore to ingot was performed in harmony with a larger cosmic order. The knowledge of alloy ratios and furnace temperatures was sacred, protected within guilds or families, passed down through initiation as much as instruction. To know the ritual was to know the craft. This sacred dialogue extended to the very earth itself. To remove a monumental limestone block from a quarry was not merely an extraction, it was a negotiation. Many cultures believed mountains and rocks were alive, inhabited by spirits. Before the first chisel struck, a ceremony might be performed to honor the spirit of the place, to apologize for the wound, and to explain the noble purpose for which the stone was taken. In ancient Egypt, the ritual of presenting the fields may have been performed at quarries, symbolically offering compensation to the earth for what was removed. This practice reflects a profound understanding of reciprocity. It acknowledged that technology came at a cost, a removal from the natural world, and that this cost required acknowledgement and balance. The stone was not a passive resource, but an active participant in a covenant. By ritualizing the quarrying process, the builders integrated their ambitious projects into the existing spiritual landscape, transforming an act of environmental alteration into one of respectful partnership. The most poignant fusion of ritual and technology is found in the obsidian blade destined for ceremony. The act of pressure flaking such a blade was itself a sacred meditation, each controlled fracture a step in shaping a tool that would serve as an intermediary between worlds. This blade was not for harvesting or combat. Its sharpness was for a different kind of precision, a spiritual one. In Mesoamerican traditions, the obsidian sacrificial knife, or tekpatl, was a revered object. Its creation from volcanic glass, the blood of the earth, and its subsequent use in ceremonial practices was a complete cosmological circuit. The technology produced the instrument, and the ritual applied it within a framework of renewal, sacrifice, and communication with the gods. The flint knapper was not just a craftsman, but a priest of form, preparing a key for the most solemn of locks. This widespread ritualization served a brilliant, multifaceted purpose in stabilizing and advancing early societies. First, it acted as intellectual property protection. By wrapping technical processes in ceremony and restricting them to initiated guilds, societies safeguarded valuable, hard-won knowledge about smelting temperatures, alloy compositions, and quarrying techniques. This prevented the dilution of expertise and maintained high standards. Second, it provided a vital metaphysical framework. Before the language of chemistry or physics existed, ritual offered a narrative to explain why combining certain rocks with fire produced liquid metal, or why a stone fractured in a predictable way. It gave meaning to the mysterious, allowing people to work confidently with powerful, poorly understood forces. Finally, and perhaps most importantly, it seamlessly integrated the act of technological innovation into the social and cosmic order. Building a pyramid or forging a king's sword was not just a civic project or a commission. It was a duty to the gods, an act that sustained the universe. This provided the motivational engine for projects that spanned generations. The labor was sanctified. In this light, the ancient perspective feels suddenly, strikingly contemporary. Our modern sustainability movements are, in essence, striving to reclaim a version of this sacred dialogue. The call to honor materials, to understand their full life cycle, to source ethically, and to build with circularity in mind, echoes that ancient sense of reciprocity with the natural world. We are relearning that technology divorced from a framework of respect and responsibility is ultimately fragile. The ritual may be gone, but the underlying principle remains true. The most enduring innovations are those that see the material world not as a warehouse to plunder, but as a partner in a continuous, careful conversation. That sacred dialogue with the earth was a practical necessity. Ancient technological systems were not separate from their environment. They were deeply embedded within it, creating a model of sustainability born from direct consequence. Every quarry, every mine, and every forge existed in a delicate balance with the local landscape. The scale of their consumption, while immense to our eyes, was ultimately bounded by the limits of human and animal muscle, the reach of trade routes, and the regenerative capacity of nearby forests for fuel. This created a built-in feedback loop. A society could not deplete a resource faster than it could physically extract and transport it, a constraint that forced long-term thinking. The ancient copper mines of Timna in the Negev Desert, for example, show evidence of careful, phased extraction over centuries, not rapid exhaustion. Miners followed the richest veins, leaving lower-grade ore behind, a practice that today we might call resource management. This was not necessarily a conscious environmental policy, but a pragmatic adaptation to the energy equation of their time. The true cost of technology was measured in calories, the food needed to feed the workers and the animals that hauled the stones. This tangible cost incentivized efficiency and minimal waste at every stage. A broken bronze tool was not thrown away, it was melted down and recast. A misshapen obsidian core was reduced to smaller flakes. Limestone chips from a construction site became rubble for roadways or filler for walls. In a very real sense, ancient material culture was often circular by necessity. The concept of waste was a luxury their energy budget could not afford. This intimate relationship with limitation fostered a form of embedded sustainability, where innovation was directed toward doing more with less, and where the life cycle of a material was often a closed loop within the community's reach. Their legacy challenges our modern assumption that progress must be linear and consumptive, reminding us that some of the most resilient systems are those that recognize their own boundaries. That deep partnership with the earth was not without its cost. Every technological leap from the first bronze ingot to the grandest pyramid left a mark upon the landscape. The quest for copper and tin opened deep wounds in the earth as mines followed veins of ore into hillsides. To feed the insatiable furnaces, forests were felled for charcoal on a scale that could transform local ecosystems. The quarry faces for limestone, once living cliffs, became sheer, white scars against the green. We can see in these ancient sites the early contours of an environmental footprint, a reminder that innovation has always required an exchange with the natural world. Yet within this evidence, we also find something surprising, not just exploitation, but the faint outlines of conscious management. At the Great Orme copper mines in Wales, one of the largest prehistoric mines in Europe, archaeologists see not chaotic digging, but a remarkably systematic operation. Tunnels were carefully propped with timber, following the richest seams with efficiency, and some shafts show signs of being deliberately backfilled with waste rock once exhausted. This suggests a practical understanding of stabilizing the worked landscape, perhaps to prevent collapses or to reclaim the area for other uses. It was a rudimentary form of land stewardship, born from direct experience and a need for safety and order. The efficiency of ancient craft often turned necessity into a virtue of conservation. Consider the Obsidian worker's toolkit. From a single fist-sized core of volcanic glass, a master flint-knapper could produce dozens of razor-sharp blades, each flake removed with such precision that the leftover material, called debitage, was often reduced to tiny, unusable chips. The waste was minimal by design because the material was precious and the journey to obtain it long. This principle of maximizing yield from a finite resource echoes through their material culture. And when a bronze tool broke or a stone wall crumbled, the common response was not disposal but renewal. A fractured bronze axe was not thrown away, it was returned to the crucible, its metal reborn in a new form. Limestone blocks from a toppled temple or an obsolete fortification were carefully salvaged to build the next generation's church, castle, or home. The Roman Empire was particularly adept at this, often repurposing the stones of conquered civilizations for their own monuments, a physical layering of history. This culture of repair and reuse was driven by the sheer energy investment required to create these materials in the first place. The durability of bronze and stone meant objects were made to last, and their longevity fostered a mindset where things were maintained, adapted, and valued across lifetimes. These ancient cycles of extraction, use, and reuse offer us a critical, long-term mirror. Our modern world is built on a vastly accelerated version of the same processes, but with one profound difference: our capacity to extract and consume has far outpaced those natural and logistical constraints that once enforced balance. We mine at scales unimaginable to Bronze Age smiths, and our products are often designed for a short life in a linear journey from factory to landfill. The ancient model, born from limitation, points toward a different philosophy, one of circularity. It suggests that sustainability is not a new idea, but perhaps a very old one temporarily forgotten. Their legacy challenges us to ask, what if we designed our own bronze and limestone, our plastics and alloys, with that same inherent value of longevity and recoverability? The scars on those ancient landscapes are lessons in consequence, but the careful mining and the repurposed stones are lessons in resilience, showing that even the earliest technologies contained the seeds of responsibility. A polished bronze mirror eventually tarnishes. The sharpest obsidian blade left in the soil slowly turns to dust, and even the mightiest limestone wall will one day crumble back into the earth. This is the quiet truth of all human creation, a slow return to the elements from which it came. For centuries, even millennia, the greatest technological feats of the ancient world simply vanished, buried under layers of silt, sand, and forgetting. The very materials chosen for their permanence became prisoners of time, their stories locked away. This is where our modern journey to understand them truly begins, not in the moment of their glorious use, but in the long silence that followed. The grand narrative of bronze, obsidian, and limestone was fractured into a billion forgotten fragments. A rusted bronze pin here, a scatter of black glass flakes there, a single carved stone peeking from a farmer's field. The task of reassembling this puzzle falls to a discipline that acts as both detective and translator, archaeology. Its role is not to dig up treasure, but to listen to the whispers of decay. Every patina on copper, every microscopic wear pattern on an obsidian edge, every tool mark left on a quarry wall is a word in a lost language. Archaeology teaches us to read the biography of objects, to understand not just what they were, but the lives they touched and the processes they endured. When an archaeologist brushes the dirt from a bronze chisel, they are asking a cascade of questions. What is the alloy made of, and what does that tell us about trade networks? How is the edge worn down, and does that reveal it was used for woodworking or stone dressing? Was it found in a workshop, a tomb, or a home, and what does that context say about its value? Each answer is a thread, and slowly, painstakingly, these threads are woven back into the fabric of a civilization's technological mind. The true legacy of these materials was preserved not in libraries, but in their own gradual, physical transformation. Their decay became their memory. That slow return to the earth is why this legacy remained hidden for so long. The beautiful green patina on a bronze statue is actually corrosion, a chemical conversation with the air that can, over centuries, completely consume the metal beneath. The polished obsidian mirror, if dropped and shattered, becomes just another layer of black flakes in the soil, indistinguishable from natural debris. And the crisp hieroglyph carved into limestone softens with each passing rain, its message blurring into the stone's own weathered face. Time did not just bury these objects, it actively unraveled them, turning grand technologies back into anonymous fragments of copper, glass, and rock. The wooden handles of tools rotted to dust, the leather straps that bound stone to sledges dissolved, and the very memories of how these things were made faded from oral tradition. This left behind a world of silent, scattered clues, a billion-piece puzzle with most of the pieces missing and no picture on the box to guide us. Reassembling that puzzle required the invention of a new kind of technology, one designed not to build but to listen. This is the science of archaeology, a meticulous method for hearing the whispers left in the physical remains. Archaeology does not dig up stories, it decodes them. It is a forensic toolkit for the long term. The first and most fundamental tool is stratigraphy, the simple but profound law that generally, what is on top was laid down more recently than what is below. By carefully excavating layer by layer, archaeologists can create a vertical timeline of a site. A bronze spearhead found in a layer of ash and burned debris tells a different story than an identical spearhead found in a layer of rich soil alongside pottery and animal bone. The context is everything. To attach actual dates to these layers, science provides clocks. Radiocarbon dating measures the decay of a radioactive isotope in any once living material, like charcoal from an ancient forge or seeds found in a workshop floor. This can tell us within a range when that fire burned or when those people lived, but the clues get even finer. Residue analysis uses chemistry to detect microscopic traces left on artifacts. That shiny obsidian blade might, under a microscope, reveal minuscule streaks of plant silica, telling us it was last used to harvest reeds. A seemingly empty ceramic pot from a bronze workshop might still hold invisible fingerprints of the animal fats used to lubricate molds. These techniques transform silent objects into chatty witnesses. Perhaps the most powerful tool in this kit is experimental replication. This is where archaeologists stop being just scientists and become apprentices. To truly understand the pressure flaking of obsidian, they must sit for hours with antler tines and glass cores, feeling their way toward that perfect fracture, recording how long it takes, how many failures occur, and what muscles ache. To comprehend the movement of a 10-ton limestone block, they build sledges, mix lubricants, and recruit teams of volunteers to pull, learning through sweat and physics what the ancient energy budget truly required. This hands-on work bridges the gap between the artifact and the artisan. It reveals the hidden knowledge in the body, the skills that were never written down because they were written into muscle memory and tactile intuition. Each experiment, each soil sample, each isotopic analysis of bronze adds a single pixel of data. A workshop floor plan shows the layout of furnaces and casting pits. The precise angle of a tool mark on a quarry wall reveals the type of chisel used and the direction of the strike. The chemical signature of tin in an alloy can be matched to a specific mine across a continent. Alone, these pixels are meaningless, but collected by generations of researchers across the globe, they gradually coalesce into a picture. We don't find a manual titled How to Build a Pyramid. Instead, we compile 1 million tiny facts about quarry geology, sled friction, ramp incline, and worker diet. From this mosaic, the narrative of the technology emerges. This process of rediscovery is itself a brilliant human innovation, a systematic technology for recovering lost wisdom. It is our way of leaning close to the materials themselves and asking softly, what happened here? The answer is never a shout, but a whisper pieced together from a universe of fragments. The whispers of those ancient workshops never truly fell silent. They resonate in the most unexpected corners of our modern world, proving that the principles forged in bronze, obsidian, and limestone are not relics but a living foundation. The monomolecular edge of an obsidian blade, for instance, never became obsolete. It simply evolved. In the 1980s, a researcher named Dr. Don Craven made a startling discovery. He found that obsidian scalpels, when used in delicate eye and cosmetic surgery, produced incisions so clean they healed with significantly less scarring than even the finest steel. The ancient material, it turned out, had a biological advantage modern metallurgy had overlooked. Today, specialized surgeons still use obsidian blades for procedures where minimizing tissue trauma is paramount, a direct technological lineage stretching back thousands of years. But the echo is louder in the principle, not just the material. The quest for that perfect, sharp edge drives modern material science toward ever thinner, stronger substances. We see it in the diamond-tipped drills that bore through solid rock, and in the silicon wafers etched with circuits only a few atoms wide. The ancient flint knapper, guiding a fracture with precise pressure, was pioneering the same concept of controlled removal that now builds our microchips. Their technology was the prototype for our nanotechnology. This principle of combining materials, so brilliantly demonstrated in bronze, defines our contemporary world. We no longer work with just a few elemental metals. We engineer entirely new substances. Carbon fiber is a perfect echo of this ancient synergy. Alone, a strand of carbon is fragile. But when those strands are woven into a matrix and set within a polymer resin, they create a composite material that is incredibly strong, lightweight, and rigid. This is the direct philosophical descendant of the bronze alloy. It is the act of taking two ordinary components and combining them intelligently to create a third with extraordinary, tailored properties. We use carbon fiber for the same reasons ancient cultures prized bronze, for its superior performance. It builds aircraft that can defy gravity with less fuel, racing bicycles that transfer energy with ruthless efficiency, and prosthetic limbs that are both durable and feather-light. The material has changed, but the cognitive leap is identical. We are still that ancient smith at the crucible, asking how we can make something better than what nature provides alone. Even the sacred dialogue with materials finds a new expression in our growing focus on sustainability. The ancient model of circularity, born from necessity, is now a conscious design goal. Modern architects and engineers look at materials like cross-laminated timber, an engineered wood product stronger than steel for its weight, and see not just a building component, but a carbon sink. They design buildings for disassembly where components can be unfastened and reused, mirroring the ancient practice of repurposing limestone blocks. The concept of a building's embodied energy, the total energy consumed in its material extraction, transport, and construction, is a modern metric for that ancient, intuitive understanding of cost. We are beginning to measure our technological footprint with the same pragmatic awareness that guided the quarry master, not out of ritual, but out of a dawning recognition of global limits. The conversation has shifted from appeasing Earth spirits to preserving planetary systems, but the core acknowledgement remains that innovation cannot exist in a vacuum. It is part of an exchange. Perhaps the most profound echo is in the way we think. The cognitive toolkit sharpened by ancient craftsmen is now the bedrock of our digital age. The pattern recognition honed by watching molten bronze now trains artificial intelligence algorithms to diagnose illnesses from medical scans. The three-dimensional visualization required to flake an obsidian blade is the same skill used by engineers to design complex machinery in virtual reality spaces before a single part is machined. And the abstract, systems-level thinking needed to coordinate a pyramid's construction is directly analogous to the project management software that orchestrates global supply chains and space missions. We have externalized and amplified these cognitive skills with computers, but the fundamental mental architecture was built by hands working directly with stubborn, physical stuff. Our smartphones may seem a universe away from a limestone quarry, but they are both products of the same evolved human mind, a mind that learned to solve problems by manipulating the material world. The legacy is not in the objects we find in museums, but in the very way we perceive and shape reality. Every time we solve a complex problem by breaking it into parts or design a new material for a specific function, we are speaking the ancient language of bronze, obsidian, and stone. It is the mother tongue of human ingenuity. That monomolecular edge is not a museum curiosity. It is in an operating room, in specialized fields like ophthalmic and cosmetic surgery, where the slightest scar can alter a life. Modern surgeons sometimes choose a tool from the deep past. They reach for a scalpel made from obsidian. The volcanic glass can still be honed to an edge hundreds of times sharper than the finest surgical steel, allowing for incisions so clean they promote faster healing and minimize visible scarring. This is not a historical reenactment. It is a clinical choice based on superior performance, a direct technological lineage from the flint knapper's hands to the steady grip of a modern healer. The principle of the lost wax process lies with even more spectacular consequences. Look inside the heart of a modern jet engine, at the turbine blades that must withstand temperatures hot enough to melt most metals. These are not simple metal casts. They are intricate, single crystal forms, often hollow and filled with complex internal cooling channels, and they are created using a direct descendant of the ancient lost wax method. An exact wax model of the blade, complete with its internal labyrinth, is coated in ceramic to create a mold. The wax is melted out, and molten superalloy is poured in. When the ceramic shell is broken, a perfect metal duplicate of that wax original emerges, ready to help power an aircraft across continents. This ancient technique for capturing complex form is now essential for one of our most advanced transportation technologies. Even the humble binding agent of limestone finds a revolutionary echo. For centuries, researchers have puzzled over the durability of Roman concrete, which seems to grow stronger in seawater while our modern concrete crumbles. The secret, we now know, was a recipe that included volcanic ash. This reactive ingredient created a crystalline structure that actually self-healed tiny cracks. Today, inspired by this ancient formula, scientists are developing new generations of green cement that not only mimic this durability, but are designed to actively pull carbon dioxide from the atmosphere as they cure, turning our built environment into a carbon sink. This is not mere imitation, it is learning the language of an old master to write a new, more sustainable chapter. And that fundamental spark of innovation, the act of intelligent combination first seen in the bronze alloy, is the very soul of modern material science. We no longer just find or smelt, we design from the atomic level up. Carbon fiber and fiberglass are pure expressions of the composite principle. By embedding strong, stiff fibers within a resilient resin matrix, we create a new substance that is lighter and stronger than steel, revolutionizing everything from aerospace to sporting goods. We are not inventing new paradigms so much as we are rediscovering ancient ones with a deeper vocabulary. The ancient artisan looked at copper and tin and saw a better axe. We look at carbon atoms and polymers and see a better wing. The conversation between human intention and material potential never ended. It simply accelerated, speaking now in the languages of chemistry, physics, and digital design, but still answering the same eternal question: how can we build a better world from the pieces we are given? The mastery of materials demanded a new kind of mind. This brings us to the sixth great technological leap, the conceptualization of the master craftsperson. This was not merely a title for someone who was good with their hands. It represented a profound societal evolution, the recognition that deep, specialized knowledge was a form of capital more valuable than the raw materials themselves. The master was a living library. They held in their memory the exact feel of a 9-to-1 bronze alloy as it began to cool, the precise sound of a perfect conchoidal fracture in obsidian, and the subtle grain of limestone from a specific quarry that would accept a chisel without shattering. This knowledge was not written down, it was encoded in gesture, muscle memory, and sensory intuition. A society that could produce and honor such individuals was investing in its own intellectual future. The master craftsperson became the critical node where raw material, technical skill, and cultural meaning converged. They were the translator who turned community ambition into enduring form. How do you build a civilization that lasts? You begin by building the people who know how to build. The workshop of a master was more than a production site, it was an educational institution. The relationship between master and apprentice was the primary engine of technological transmission for millennia. This was not a casual teaching arrangement, it was a total immersion, often beginning in childhood. The apprentice did not start by learning theory. They began by doing the most mundane tasks, sweeping the forge floor, gathering charcoal, or sorting quarry stone by size. This was not exploitation, but a foundational lesson. It taught respect for the process, an understanding of the ecosystem of materials, and it allowed the novice to absorb the rhythms and rituals of the craft through constant, passive observation. They learned the master's posture at the anvil, the specific way they held a pressure flaker, the exact tone of their voice when instructing a team moving a stone. This knowledge transfer was holistic, engaging all the senses. the apprentice learned to judge the temperature of bronze by the color of the glow in a dim workshop, a skill no textbook could ever convey. They learned the smell of limestone dust mixed with water, a sign the cutting was going well. They developed the calloused touch to feel a nearly invisible flaw in a polished obsidian mirror. This education was slow, deliberate, and deeply personal. It ensured that the most subtle, unspoken aspects of the craft, the true art of it, were passed down intact. The goal was not to produce a copy of the master, but to forge a new master who could one day innovate within the tradition. This system created lineages of expertise, guilds and families who guarded their methods not out of mere secrecy, but from a profound understanding that this knowledge was hard-won, fragile, and essential to the community's identity and survival. The master craftsperson was thus both a conservator of the past and an innovator for the future, their hands serving as the living link in an unbroken chain of ingenuity. That master craftsperson stood at a powerful intersection in society. They were the living bridge between the raw potential of the earth and the refined ambition of civilization. To command the secrets of bronze, to read the soul of an obsidian core, or to direct the placement of a megalith, was to wield a form of power that was both practical and mystical. This was not the fleeting power of a warrior or a ruler, but the enduring power of one who could make the impossible tangible. Their expertise, therefore, did not exist in a social vacuum. It elevated them. In an era before formal degrees, mastery was the ultimate credential, earned through a lifetime of silent observation, failed attempts, and hard-won success. This knowledge granted them a unique status. They were consulted, revered, and often richly rewarded. The architect of a successful temple or the smith who forged a king's ceremonial sword was not just a contractor, they were a partner in the ruler's legacy. Their skill became a form of social currency, translating technical ability into respect, influence, and sometimes even a form of immortality, as their names were occasionally recorded alongside their creations. This established a profound archetype, the idea that deep, specialized knowledge was a communal asset worthy of protection and honor. The master was not just making things, they were safeguarding the very capacity for civilization to renew and advance itself. This path to mastery was never a solitary journey. It was a slow, deliberate immersion, a transfer of wisdom that flowed through the most intimate of channels, the relationship between master and apprentice. This was the ancient world's most robust educational system, built not on lectures but on lived experience. An apprentice, often beginning as a child within a family workshop, did not start by learning theory. They began by absorbing the environment. Their first years were spent in service to the process, gathering charcoal for the forge, hauling water to keep a limestone saw's abrasive slurry wet, or sorting flakes of obsidian debitage. This menial work was foundational. It taught a visceral respect for the materials and the energy required to transform them. More importantly, it placed the novice in a state of constant, passive learning. They heard the master's muttered judgments about the quality of an ore, saw the exact angle of their wrist when applying pressure to a stone core, and felt the collective rhythm of a team moving a massive block. Knowledge was transmitted through the senses long before it was ever explained with words. The master craftsperson was teaching a language of touch, sight, and sound. An apprentice learned to judge the temperature of molten bronze by the specific shade of orange glowing in the dim forge, a skill no verbal description could ever capture. They developed the calloused fingertips to feel a nearly invisible seam in a carved limestone block. This education was holistic, embedding the craft into the apprentice's very nervous system. It ensured that the most subtle, intuitive aspects of the work, the true art of it, were passed down intact. The goal was to create not a copy, but a new master, someone who could one day innovate within the tradition itself. This system created powerful lineages of expertise, guilds, and familial workshops that guarded their methods not out of mere secrecy, but from a profound understanding that this knowledge was fragile, hard-won, and essential to the community's identity and survival. We can see this archetype crystallized in a few rare, named individuals from antiquity. In Egypt, the figure of Imhotep stands as a towering example. He was the chief architect, physician, and high priest for Pharaoh Djoser, and he is credited with designing the step pyramid at Saqqara, the world's first monumental stone building. Imhotep was so revered for his knowledge that, centuries after his passing, he was deified as a god of wisdom and medicine. His legacy demonstrates that the master craftsperson could ascend to the highest echelons of society, their technical and intellectual achievements viewed as divine gifts. While most masters remained anonymous, their influence is etched into the artifacts they left behind. The consistent perfection of Shang dynasty bronze vessels, each cast using the same intricate piece mold technique across generations, speaks to a tightly controlled guild system where recipes and rituals were closely guarded. The identical pressure flaking styles found on obsidian tools across vast regions of Mesoamerica suggest established schools of practice where a master's signature technique was replicated by their students for centuries. These individuals, named and unnamed, represent the institutionalization of innovation. Their existence signaled a societal decision, a recognition that progress depended on dedicating lives to the deep study of specific materials and processes. They were the original specialists, the human repositories upon which technological advancement depended. This ancient model of expertise established a template that runs like a bright thread through human history. It connects directly to the master artisans of the European Renaissance, figures like Leonardo da Vinci or Benvenuto Cellini, who blended artistic genius with engineering prowess and commanded the patronage of popes and kings. Their workshops functioned in much the same way as ancient ones, with apprentices grinding pigments, preparing canvases, and learning through immersion. The thread continues into the Industrial Revolution and beyond, transforming into the modern specialist, the aeronautical engineer, the materials scientist, the software architect. While the tools have changed from chisels to supercomputers, the core social contract remains strikingly similar. We still elevate and invest in those who possess deep, specialized knowledge. We still structure education around long periods of training and mentorship, moving from theory to practice. And we still understand that complex challenges, whether building a cathedral or a quantum computer, require the guiding hand of a master who can see the whole system. The respect granted to the bronze smith or the master mason was the first acknowledgement that human ingenuity, when focused and refined over a lifetime, becomes our most valuable and renewable resource. Their legacy is not just in the objects they made, but in the very idea that society thrives by honoring those who truly know how to make. Yet for all we have reconstructed, profound silences remain. The technological legacy of bronze, obsidian, and limestone is a story told in fragments, and the gaps between them hold some of our most tantalizing questions. We have decoded the recipes and mapped the trade routes, but the inner world of the ancient artisan, the silent language of their intuition, remains just out of reach. How did a master smith without a thermometer consistently judge the exact moment to pour the bronze? We can replicate the alloy, but we cannot replicate the lifetime of sensory experience that told them the molten metal was ready, a knowledge held in the eyes and the feel of the heat on the skin. That intimate, embodied wisdom evaporated the moment the last apprentice of a tradition passed away. Similarly, we can analyze the chemical composition of a mortar used in limestone construction, but the precise oral instructions for mixing it, the chants that may have accompanied the pouring, the specific seasonal considerations passed down through generations, are lost forever. These are not minor details. They represent the living context of the technology, the human rhythm that made the material sing. Our scientific tools can tell us what something is made of, but they struggle to tell us how it truly felt to make it, or the unspoken social agreements that allowed 100 people to pull a sledge in perfect unison. The silence is most profound around failure. Archaeology naturally favors success, the finished object that survived, but innovation is forged in mistake. We have far fewer records of the shattered molds, the collapsed ramps, the quarries abandoned because the stone quality was poor. These failures were the true classrooms, and their lessons are largely mute to us. We see the glorious pyramid, but we can only guess at the first, flawed designs that taught the architects what would not work. This missing narrative of trial and error leaves our understanding inherently incomplete, reminding us that history is written by the victories that endured, not the countless experiments that paved their way. The finished pyramid stands as a testament to what we can understand, but its construction process remains a conversation with the unknown. For all our advanced tools and theories, we still debate the exact mechanics of raising the Great Pyramid's final, multi-ton capstone. The precise overland paths for Anatolian obsidian to reach distant villages are still being traced, one chemical signature at a time. Metallurgists puzzle over Bronze Age artifacts that show a mysterious, almost stainless corrosion resistance, hinting at alloy recipes or surface treatments we have not yet replicated. And the cognitive blueprint behind the celestial alignments of stone circles, the complex geometry encoded without written plans, continues to challenge our digital models. These are not failures of investigation, but persistent echoes. They remind us that the ancient innovators operated within complete knowledge systems, many of which were oral, intuitive, and framed within a worldview fundamentally different from our own. Their technology was woven into a fabric of ritual, environmental perception, and hands-on wisdom that rarely survived in a form our instruments can measure. We can analyze the stone, but we cannot interview the mason who felt its grain. We can date the bronze, but we cannot sit with the smith who knew the perfect pour by the color of the flame. These gaps are humbling. They suggest that their sophistication was holistic, a seamless blend of technical skill and cultural intelligence that our more compartmentalized sciences are still learning to see as a whole. The silence around their methods is not an empty space, but a resonant chamber asking us to listen differently, to consider that some forms of knowing are transmitted through the hands and the heart, not just through texts and equations. Our journey to understand them, therefore, is not a puzzle to be solved and closed, but a continuous dialogue with the past, one that keeps the legacy alive by forever finding new questions in the old stones. A tool that never breaks is a fantasy, but a society that can fix anything is a civilization. This brings us to the seventh, and perhaps most underappreciated, technological leap, the deliberate invention of maintenance and repair. It is a quiet revolution that transformed technology from a fleeting event into a continuous relationship. The first time a person looked at a cracked bronze axe head not as trash, but as a problem to be solved, they crossed a critical threshold. They moved from being consumers of objects to stewards of systems. This mindset recognized that the true value of a technology lay not just in its brilliant creation, but in its sustained usefulness across a human lifetime and beyond. Maintenance is the long conversation we have with the things we build. a dialogue of care that fights against the relentless pull of entropy. In a world where energy and raw materials were precious, letting a perfectly good bronze tool be discarded because of a loose handle or a dull edge was an unaffordable waste. Repair was not an option, it was an imperative. This practice required a different kind of knowledge than creation. It demanded diagnostics, the ability to look at a failed object and understand not just what was broken, but why it broke and how to restore its function without starting from scratch. It fostered a culture of resourcefulness where every fragment had potential. A shattered stone quern for grinding grain might have its broken pieces carefully drilled and clamped back together with metal staples, a process known as clamping or cramping, giving the heavy object many more years of service. This was not about making do, it was about making last. The development of standardized parts, though primitive by our standards, was a direct offspring of the repair mentality. If the wooden handle of a bronze adze was designed to fit a socket of a specific size and shape, then a broken handle could be replaced without needing a master smith to recast the entire metal head. This interchangeability, this modular thinking, meant that technology could be decentralized. A village carpenter could maintain the community's tools, relying on a supply of pre-shaped handles, while the rare and valuable bronze components circulated for generations. Repair built resilience into the very fabric of daily life. It acknowledged a simple, profound truth that things fall apart, and a society's strength is measured by how patiently and how cleverly it puts them back together. The true test of a technology is not its brilliant debut, but its long, quiet life of service. Ancient societies understood this intimately, building entire philosophies around the care and preservation of their material world. They did not see a cracked bronze axe or a chipped obsidian blade as a final failure, but as the next chapter in the object story. This commitment to maintenance was a sophisticated technological practice in its own right, a continuous dialogue with the things they had created. A bronze sword was not a static possession. Over its lifetime, its edge would be honed down again and again, the metal growing thinner but sharper with each careful grinding on a whetstone. When the wooden hilt rotted or splintered from the impact of battle, it was not discarded. A craftsperson would skillfully remove the old remnants, clean the tang, the metal tongue of the blade, and fit a new handle of ash or oak, securing it with rivets and bindings. If the blade itself snapped in combat, the fragments were sacred. They were returned to the forge, melted down in the crucible alongside fresh ingots, and reborn as a new tool, perhaps a chisel or a spear point, its metallic essence living on in a different form. This cycle of use, wear, and renewal was built into the very concept of the object. Its value was not disposable, it was cumulative, growing with every repair. Obsidian demanded an even more delicate kind of stewardship. A razor-sharp blade, once dulled, could not simply be sharpened like metal. Instead, a craftsperson would engage in a process called re-knapping. Using the same precise pressure flaking technique, they would remove a series of tiny flakes along the dulled edge, peeling away the worn material to reveal a fresh, monomolecular edge beneath. This could be done multiple times over the tool's life, each session shortening the blade slightly but restoring its lethal sharpness. When an obsidian blade became too small for its original purpose, it was often inset into a new setting. A mosaic artist might take dozens of these small, retired flakes and set them into a bed of resin on a wooden pectoral, creating a shimmering ceremonial garment. A carpenter might glue a tiny, still sharp fragment into the end of a wooden stylus for fine incising work. Nothing was wasted. The material's journey was a cascade of purpose, from primary tool to secondary ornament to tertiary abrasive, until it was literally dust. The maintenance of limestone architecture was a communal ritual, a contract with eternity. the gleaming white casing stones of the Great Pyramid did not stay perfect by accident. Teams of workers would regularly inspect the vast faces, patching cracks with a mortar made from gypsum and limestone dust, and refacing areas worn by wind and sand. In monumental structures across the ancient world, plaster was the key to preservation. A finish of lime plaster made from burned and slaked limestone was applied to walls. This layer protected the softer stone beneath from water erosion, and it provided a smooth, renewable canvas for painted murals and inscriptions. When the plaster faded or cracked, it was not a sign of decay, but an invitation. A new layer would be applied, and the stories would be repainted, each renewal an act of cultural remembrance, literally layering the present upon the past. This practice required a deep, practical understanding of material fatigue, of how stone weathered, how joints settled, and how to make repairs that were both structurally sound and visually seamless. This pervasive culture of repair points to a profound worldview, one that saw objects as having lifespans that could be actively extended through skill and care. It was a perspective rooted in the tangible economics of energy, the effort required to mine tin, to trade for obsidian, or to quarry and move a single block of limestone was so immense that discarding the finished product was unthinkable. This constraint fostered genius. It led to innovations in joinery like the mortise and tenon, which allowed wooden components to be replaced without damaging stone or metal. It advanced the chemistry of surface treatments, like the waxes and oils used to protect bronze from corrosion, or the mineral pigments mixed into plasters for durability. Maintenance was not a menial task. It was the highest form of respect for the labor embedded in every object and for the resources of the earth itself. When we hold a modern device designed to be obsolete in 2 years, or discard a tool because a single plastic part has broken, we have severed a connection that our ancestors held sacred. Their technological tradition was not about the next new thing, it was about the enduring thing. It was a practice focused on stewardship, on stretching the utility of every material to its absolute limit through cycles of attentive repair. In their relentless fight against entropy, they built a model of sustainability that was not an abstract ideal, but a daily, hands-on discipline. The legacy of their maintenance is a quiet challenge to our own age, asking us what we truly value and what we are willing to care for, not just create. The materials they mastered became more than tools, they became the very words of a culture's story. A bronze vessel was not just a container for wine, it was a statement of power and lineage. Its intricate surface, cast with motifs of dragons or ancestral symbols, communicated a family's history and their rightful place in the cosmic order. To own it, to use it in ceremony, was to participate in that narrative, to have your identity affirmed by the weight and sheen of the metal. The object itself was a kind of contract, a physical proof of status and belief that everyone in the room could see and understand. This is where technology transcends utility and enters the realm of language. The choice of material, the style of decoration, even the way an object was used, all became a coded message about who a people were and what they valued most. In a world without mass media, these crafted things were the primary broadcast system for cultural identity. They told stories of origin, of connection to the land, and of a community's unique vision of the world. A society that forged magnificent bronze drums was telling a different story about itself than one that erected towering limestone obelisks. The material became the medium, and the craft was the accent in their collective voice. We can hear this voice clearly in the contrasting stories told by bronze and jade in ancient China. For the Shang and Zhou dynasties, bronze was the material of earthly power and ritual communication with the ancestral realm. The massive ceremonial vessels, the ding and the gui, were used in solemn rites to offer food and wine to the spirits of forebears. Their imposing size and the thunderous, intricate designs of touty masks and dragons were not merely decorative. They conveyed the authority of the ruler who commissioned them, a ruler whose legitimacy depended on maintaining a proper relationship with heaven and the ancestors. To cast such an object required control over vast resources, specialized labor, and secretive technical knowledge, making the vessel itself a symbol of organized state power. Yet in the same tombs that held these bronzes, archaeologists often find exquisite pieces of an entirely different material, jade. This nephrite stone, even harder to work than bronze, requiring endless grinding with abrasives, was fashioned into by discs and Kong tubes. While bronze spoke to the ancestral spirits, jade spoke of eternity and the essence of the human soul. It was associated with purity, virtue, and immortality. A jade cicada placed on the tongue of the departed, or a suit of jade plaques sewn together with gold wire, was believed to protect the body from decay and guide the spirit. Here, two technologies, metal casting and stone grinding, served two parallel but intertwined cultural needs. Bronze managed the social and ritual order of the living state, while jade attended to the eternal journey of the individual soul. Together, in a single burial, they painted a complete picture of that civilization's worldview, its fears, its hopes, and its understanding of a universe divided between the temporal and the timeless. Across the ocean, a different stone told a story of celestial connection. For the Maya, limestone was not just a building block, it was the living skin of the earth, a canvas for chronicling time itself. Their soaring pyramid temples, like the one dedicated to Kukulkan at Chichen Itza, were precise astronomical machines. The stairways, the corners, the shadows they cast at the equinoxes, all were calculated to interact with the sun's journey. But the stone's role went deeper. The Maya erected great limestone slabs called stelae in their city plazas. On these, master carvers would inscribe intricate hieroglyphs and portraits of rulers, recording exact dates from a complex calendar system that stretched back to a mythical starting point of time. This was history written in rock, a way of anchoring a king's reign and a city's events into the eternal cycles of the cosmos. The limestone stela was a permanent claim, a statement that said, our deeds, our calculations, our understanding of the stars are now part of the geological record. It transformed a local political event into a moment of cosmic significance, weaving human identity directly into the fabric of time and the substance of the earth. The material's durability was essential to the message. They were not writing on parchment that could burn, but on the bone of the world itself, ensuring their identity would be remembered for as long as the stone endured. Even the black glass of obsidian carried a profound symbolic weight, one that could shift meaning entirely from one culture to the next. In Mesoamerica, as we've seen, it was the blood of the earth, sacred and tied to ritual. But travel to the island of Papua New Guinea, and you find a completely different story written in the same material. There, obsidian from quarries in New Britain was traded over vast sea networks to islands that had no stone suitable for tools. Here, obsidian became the ultimate social currency. A finely crafted obsidian spear, point, or dagger was not primarily a weapon for war, but a pivotal object in the complex gift exchange systems that wove communities together. To give such a blade was to offer a piece of the distant, the exotic, and the technologically marvelous. It created obligations, cemented alliances, and elevated the status of both the giver and the receiver. The obsidian's value came not from its spiritual resonance, but from its journey, its rarity, and the skill required to work it. It became a symbol of connection, of the far-reaching social networks that defined a person's place in the world. The same volcanic glass in different hands and different belief systems could symbolize divine power or social bond, a mirror for spirits or a mirror for human relationships. This tells us that the meaning was never in the material alone. It was poured into the material by the culture that cherished it. The technology provided the vessel, but the people filled it with their own unique story of who they were. This deep symbolism solved a very practical problem of social cohesion. In an era before flags, anthems, or written constitutions, how do you make 1,000 people or 10,000 feel like they belong to the same idea? Shared material culture was the answer. If everyone in a region used the same distinct style of bronze fibula or brooch to fasten their cloak, that small object became a badge of belonging. It signaled, "I am from here, I share your customs." The communal labor of quarrying and moving megaliths for a stone circle had the same effect. The shared effort, the blisters and the triumphs, physically built the monument while also building a shared identity among the builders. They were no longer just individuals from scattered farms. They were the people who raised the great stones. The technology of creation forged the community itself. Furthermore, mastering a difficult material like bronze or obsidian created a shared language of quality and aesthetics. People developed a common eye for what made a good blade, a pleasing pot, a well-built wall. This shared standard of excellence became a point of cultural pride, a way to distinguish us from them. Our bronze is finer, our obsidian work more precise, our stonework more enduring. The material legacy thus acted as both a social glue and a boundary marker, defining the group from within while differentiating it from the world outside. It was identity made solid, held in the hand, and built into the landscape. So when we look at a museum case holding a Bronze Age sword or a Mayan vase, we are not just looking at an old tool or container. We are looking at a frozen conversation. We are seeing how a group of people chose to solve problems, yes, but also how they chose to explain their world, honor their ancestors, and tell their descendants who they were. The material is the alphabet, and the craft is the grammar of a story that was too important to be left to words alone. It is a story of belonging, written in the enduring language of earth and fire. A bronze crown was not just a piece of jewelry, it was a fragment of the sun given form. In cultures from the Mediterranean to East Asia, this alloy's golden luster and its birth in the sacred fire of the forge made it the natural emblem of divine and royal authority. To wear bronze was to visibly harness the power of the heavens. The Egyptian pharaoh, often called the Golden Horus, was depicted with a bronze-sheathed crook and flail, symbols that linked his rule to the eternal cycle of the sun god Ra. In ancient China, the monumental bronze-ding vessels used in ancestral rites were not merely pots, they were the very anchors of the state, their weight and sheen a physical manifestation of the mandate of heaven. The material's durability promised that the king's authority, like the metal itself, would not corrode. This symbolic power was deliberate. By controlling the rare ingredients and secretive craft of bronze, elites controlled the visual language of power itself. The object's brilliance was a calculated statement, whispering of inaccessible knowledge and unassailable status to all who beheld it. In stark contrast, obsidian held the allure of the night. Its glossy black surface could swallow light, creating mirrors that were thought to be portals to other realms, while its edge could spill life with terrifying efficiency. This duality made it a substance of profound ambivalence, equally revered and feared. For the Aztecs, it was Itztli, the embodiment of sacrificial knives, and the god Tezcatlipoca, whose name means smoking mirror. A priest gazing into an obsidian mirror sought visions from the spirit world, an act of revelation. Yet the same material furnished the Macuahuitl, a wooden sword lined with these glass blades, capable of horrific wounds. Obsidian did not symbolize orderly, solar power like bronze. It represented the necessary chaos at the edge of the known world, the sharp truth of divination, the dangerous threshold between life and death, and the dark majesty of the star-filled sky. Its symbolism was rooted in its inherent properties, its sharpness and its darkness, which cultures interpreted as tools for interfacing with the most profound and perilous mysteries. If bronze was the sun and obsidian the night, then limestone was the enduring dawn light on a settled world. Quarried from the earth and often gleaming white when first cut, it represented purity, order, and the triumph of human intention over natural chaos. It was the blank page upon which a civilization could inscribe its laws, its history, and its claims to eternity. The choice to build a temple or a palace from limestone was a statement of permanence and legitimacy. In ancient Egypt, the pyramids of Giza, originally clad in smooth white Chora limestone, would have shone like beacons on the horizon, literally translating the pharaoh's divine authority into a geographical fact. In classical Greece, the Parthenon's marble, a metamorphosed limestone, was not just a structural choice, it was an aesthetic and ideological one, embodying ideals of clarity, balance, and democratic civic pride under the bright Mediterranean sun. The stone's surface became the trusted medium for the most important words a society could produce. Hammurabi's code, carved into a basalt stele, and the Rosetta Stone, a decree in 3 scripts, used the permanence of stone to grant their messages the weight of geological time. The material guaranteed that the word, once given form, would outlast the ruler, the dynasty, even the language itself. Therefore, to commission an object was to make a deliberate symbolic choice long before the first artisan lifted a tool. A king did not simply order a statue. He chose between bronze for solar majesty, obsidian for ritual potency, or limestone for eternal legacy. A ceremonial knife made of bronze communicated a different kind of ceremony than one made of obsidian, the former likely linked to sanctioned state ritual, the latter to the visceral interface with the sacred. This embedded meaning solved a critical social function. It made complex ideas about power, belief, and identity instantly legible. In a world with low literacy, you didn't need to read a treatise on kingship. You just needed to see the sun glint off a bronze crown. You didn't need a sermon on the afterlife. You felt the awe standing before a white limestone tomb that pierced the sky. The material itself did the talking. This semiotic layer is a vital part of the technological legacy. It teaches us that innovation is never just about solving a practical problem. It is equally about answering a symbolic one. Our ancestors were not just engineers, they were poets working in metal, glass, and stone, using the physical properties of the world to give abstract values a shape that could be seen, held, and remembered. The stories they embedded in these materials are what truly made them timeless. The most powerful technology begins as a secret. For centuries, the mastery of bronze, the art of obsidian flaking, and the logistics of monumental stonework were guarded treasures, concentrated in the hands of priests, kings, and elite guilds. This knowledge was power, literally. It created a world where the finest tools, the sharpest blades, and the most enduring monuments were symbols of a stratified society, where access to innovation defined your place within it. But technology, by its very nature, resists staying locked away. The seventh and perhaps most transformative leap was not a new material, but a social shift, the slow, inevitable democratization of these tools from the elite to common use. This was the moment when the sacred knowledge of the forge and the quarry trickled down, when the bronze chisel moved from the royal workshop to the village smithy, and when the obsidian blade became a farmer's sickle as well as a priest's knife. This shift did not diminish the technology. It multiplied its impact, weaving innovation into the very fabric of daily survival and setting the stage for every technological revolution to come. The first crack in the elite monopoly often came from the most practical of places, surplus. As mining and smelting techniques improved, bronze production could eventually outpace the demand for ceremonial weapons and royal regalia. Suddenly, there was metal left over. This surplus created a new economic reality. An ingot of bronze was no longer just a sacred substance, it was a commodity. It could be traded, sold, or bartered. A local chieftain or a wealthy merchant, not just a king, could now commission a bronze cauldron for their hall. A successful farmer might trade a season's surplus grain for a durable bronze plowshare, an investment that would make next season's harvest even more abundant. This trickle-down effect transformed the social meaning of the material. Bronze began its journey from being a symbol of divine right to becoming a driver of economic prosperity. The village blacksmith, once perhaps only repairing tools, now gained access to bronze ingots. They learned to recast broken items, to make simple fittings for carts and doors, and to produce robust farming implements. The technology was being adapted, simplified, and applied to the problems of everyday life. A bronze sickle was far more efficient than a flint one, lasting longer and cutting cleaner, which meant more grain gathered with less effort. This increased agricultural productivity didn't just feed people, it freed them. It created surplus time and labor that could be directed toward other crafts, trade, or community projects. The elite's technology, in the hands of the many, became an engine for lifting entire societies. This diffusion was mirrored in the world of stone. The grand, state-sponsored quarrying operations for pyramids and temples demonstrated the principles of large-scale extraction. That knowledge didn't vanish. It filtered into regional and local practice. Communities learned to identify useful local stone deposits, not for monuments to gods, but for foundations for homes, for boundary walls, and for communal grain silos. The techniques for dressing stone with bronze chisels and abrasives, once reserved for temple walls, were adapted to create precisely fitted millstones for grinding flour, or smooth, durable hearthstones for the family fire. Even the principle of the lever and ramp, used to move 100-ton blocks, was scaled down to help farmers clear boulders from fields or construct sturdy bridges over local streams. The technology of monument building became the technology of infrastructure. It moved from serving a singular, awe-inspiring purpose to solving 1,000 small, essential problems that made daily life more secure, efficient, and connected. A well-built stone bridge didn't just cross a river, it linked markets, allowed for the exchange of ideas, and strengthened the bonds between neighboring villages. The democratization of limestone was the democratization of permanence itself, allowing common people to build a lasting legacy into their own landscape. Obsidian's path followed a similar, yet uniquely intimate trajectory. While the finest ceremonial mirrors and sacrificial blades remained in the realm of the priestly class, the core technology of pressure flaking was remarkably portable. It didn't require a massive furnace or a quarry crew, just a skilled hand, a core of glass, and a simple antlered tine. This meant the knowledge could travel with people. As trade networks expanded, not only did the raw obsidian move, but the skill to work it likely did too. A traveling craftsman or a knowledgeable trader could demonstrate the basics in a new village. Soon, local artisans were producing their own blades, tailored to local needs. That incredibly sharp edge, once reserved for the body of the king or the rites of the gods, was now used to shape arrowheads for hunting, to scrape hides for clothing, to carve intricate patterns into wooden bowls, and to perform basic medical procedures within the family. The obsidian blade became a multi-tool of the ancient world, its value measured not in its ritual potency but in its sheer, versatile utility. This widespread adoption had a fascinating effect. It created a feedback loop of innovation. A farmer using an obsidian sickle might discover a better angle for the blade. A woodworker might develop a new hafting method to prevent the delicate glass from snapping. These small, incremental improvements, born from daily use by countless hands, refine the technology in ways the elite artisans, focused on ceremonial perfection, might never have considered. The common user became an innovator. This great democratization was not a peaceful, voluntary handover. It was often driven by the most pragmatic of forces, economic pressure, and the diffusion that follows conflict or trade. When empires fell or trade routes were disrupted, specialized craftspeople sometimes dispersed, taking their knowledge with them into new communities. A bronze smith whose royal patron was gone might set up shop in a market town, selling his skills to anyone who could pay. The secret recipes of the guild, once so tightly held, began to spread out of necessity. Furthermore, the very success of elite technology created its own demand. When people saw the advantages of a bronze-tipped plow, they wanted one. This market demand incentivized production outside of strict royal control. Independent workshops sprang up, competing on price and practicality rather than ritual adherence. They might produce a simpler, sturdier axe with less ornate decoration, but one that could fell a tree just as effectively. This shift from commissioned luxury to market commodity fundamentally changed the relationship between people and their tools. An object you bought for its function, with your own surplus, carries a different kind of value than one issued by a ruler. It represents personal agency, choice, and investment in your own prosperity. The ultimate legacy of this great democratization is the world we live in now. Every time you use a mass-produced tool, access information on a personal device, or benefit from a widely available medical treatment, you are experiencing the end result of this ancient process. The democratization of bronze, obsidian, and limestone set a precedent that the most powerful innovations are those that escape the vaults of the privileged and become woven into the commonwealth of human capability. It established that progress is not a vertical ladder with a few at the top, but a widening circle where each new tool, once it becomes accessible, raises the platform for everyone. This shift turned technology from a spectacle that inspired awe into a toolkit that empowered action. It moved the question from what can our leaders build for the gods to what can we build for ourselves, for our families, for our future. The silent, stubborn journey of the bronze plowshare from the royal storehouse to the farmer's field is one of the most important stories in human history. It is the story of innovation finding its true purpose, not in the service of power, but in the hands of the people. That farmer's bronze plowshare did not just cut soil, it cut through social barriers. Over centuries, a quiet but monumental diffusion took place. The technologies forged for gods and kings began a slow migration into the hands of the many. This was not a sudden revolution, but a gradual seepage like water finding its way through stone. The bronze that once formed only the crowns of pharaohs and the swords of heroes began to appear in far humbler forms. In village workshops, smiths learned to cast sturdy sickles, durable fishhooks, and simple cooking cauldrons. A metal once synonymous with divine authority was now hanging over a family hearth or tilling a field. This shift had a tangible, profound effect on daily survival. A bronze-tipped plow could break ground that stone or wood could not, turning marginal land into productive fields. A bronze sickle harvested grain more cleanly and with less loss, meaning more food from the same effort. These were not just better tools, they were engines of economic stability. They increased the yield from a family's labor, creating a surplus that could be traded, stored, or used to weather a poor season. The elite symbol of power had become the common person's foundation for resilience. The same journey transformed the sacred volcanic glass. Obsidian blades, once reserved for the solemn rituals of priests and the ceremonies of rulers, found new purpose in the rhythm of daily chores. That monomolecular edge, capable of interfacing with the spirit world, proved equally miraculous for slicing through tough fibers, scraping hides for leather, or carving intricate patterns into a wooden bowl. A hunter might now fletch his arrows with a sliver of obsidian, achieving a cleaner cut for the feather binding. A weaver could use a razor-sharp flake to trim threads on a loom with precision. In the home, obsidian became the ultimate precision tool for tasks requiring a clean, controlled cut. This demystification did not strip the material of its value, it multiplied its utility. The knowledge of pressure flaking, once a guarded priestly skill, spread along those ancient trade routes, taught in villages far from the volcanic peaks. The blade's value was no longer measured solely by its connection to the gods, but by its relentless sharpness in the service of everyday life. It became a democratized marvel, its power accessible to anyone with the skill to wield it. Even the most monumental of materials found its way down to earth. The limestone that built pyramids and temples, that proclaimed the eternal glory of kings, began to be sourced for foundations of a different scale. Communities learned to identify local deposits of workable stone. They employed scaled-down versions of the quarrying techniques they had seen or heard about, using levers, sledges, and communal labor to extract blocks for their own needs. This stone was not for monuments to eternity, but for markers of belonging and security. Farmers used it to build robust boundary walls, clearly defining fields and preventing disputes. Villages constructed communal grain silos from fitted limestone blocks, protecting their harvest from pests and weather. And for those who could afford it, a house built on a stone foundation, with stone corners and a stone hearth, represented a new level of permanence and comfort. It was a declaration that this family, this home, was here to stay. The technology of immortality was repurposed for generational stability. This great democratization did more than just distribute better tools, it fundamentally reshaped the social fabric. When a farmer could invest in a bronze plow, his prosperity became less tied to the whims of a patron and more a product of his own skill and labor. When a community could build its own secure granary, it gained a measure of independence. Access to a material culture of quality, once the exclusive domain of the elite, created a broader, more resilient middle stratum of society. People were not just subjects, they were stakeholders, building their own lasting legacies in stone and metal. This process mirrors the trajectory of our own technological revolutions with uncanny clarity. Consider the computer. It began as a room-sized, government-funded machine, accessible only to a handful of scientists and military planners. Then it shrank, entering corporate offices. Finally, it landed on our desks and now rests in our pockets, a tool for communication, creativity, and commerce for billions. The cellular network followed the same path, from bulky, expensive car phones for the wealthy to a global web connecting farmers, artisans, and students alike. In both cases, the technology started as an exclusive luxury, a symbol of institutional power, but its true transformative power was only unlocked when it escaped that exclusivity, when it was adapted, simplified, and placed within reach of ordinary people. That is when it stopped being a spectacle and started being a scaffold for new ways of living, working, and thinking. The ancient diffusion of bronze, obsidian, and limestone set this pattern in stone, proving that the most profound legacy of any technology is not in the wonders it builds for the few, but in the quiet dignity it affords the many. The democratized tools of the past are now the raw materials for our future. We stand at a fascinating frontier where the most cutting-edge research involves looking backward, not to copy, but to understand principles we have forgotten. This is the emerging field of reverse engineering antiquity, where archaeologists, material scientists, and engineers are collaborating to decode the hidden intelligence in bronze, obsidian, and limestone, seeking solutions for our most pressing modern challenges. It is a dialogue across millennia where ancient problems inspire contemporary innovation. How can a 2,000-year-old concrete formula help us build carbon-negative cities? The answer lies in the Roman harbors. For decades, scientists marveled at structures like the pier in Pozzuoli, Italy, which have spent 2 millennia submerged in the corrosive Mediterranean Sea, not crumbling but growing stronger. Modern concrete, by contrast, often fails within decades in similar conditions. The secret, researchers discovered, was not a magical ingredient, but a brilliant reactive recipe. The Romans mixed their lime mortar with volcanic ash from the region of Pozzuoli itself. When seawater seeped into the concrete, it reacted with the ash, forming rare, plate-like crystals that actually filled in microcracks as they formed. This material could heal itself. Modern teams, led by researchers at universities across the globe, have now decoded this process at the molecular level. They are not simply recreating Roman concrete, they are using its principle to design new, green cement mixes. By incorporating similar reactive volcanic materials or even industrial byproducts, they aim to create concrete that is not only more durable but actively pulls carbon dioxide from the atmosphere as it cures. Imagine a future city where the very buildings and sidewalks act as a carbon sink, their strength derived from an ancient recipe for resilience. This is not nostalgia, it is high-performance material science with a 2,000-year head start. The ancient builders, working from empirical trial and error, stumbled upon a nanotechnology they could not see, creating a sustainable material cycle we are only now learning to replicate with intention. Their limestone-based technology offers a blueprint for turning our built environment from a source of emissions into a part of the climate solution. The conversation extends from the macro to the microscopic. In laboratories today, researchers are peering at obsidian flakes under electron microscopes, not to date them, but to study the physics of their edge. That monomolecular sharpness, achieved through controlled fracture, is a masterclass in precision at the smallest scale. The question driving this research is profound. How can we design modern materials, like advanced ceramics for jet engines or medical implants, to be both incredibly hard and predictably tough? Obsidian, and the flint-knapping skill that shaped it, provides a living case study. By analyzing how a conchoidal fracture propagates through the glassy structure, scientists gain insights into how to control cracks in synthetic materials. They are learning how to design internal architectures inspired by the natural structure of volcanic glass that can stop a tiny flaw from becoming a catastrophic failure. Some are even exploring how the ancient practice of pressure flaking, a form of ultra-precise subtractive manufacturing, could inform new methods for machining microscopic components. The artisan guiding a fracture with an antler tine was performing a primitive version of what we now do with focused ion beams in cleanrooms. The goal is the same: to remove material with absolute control to reveal a perfect functional form. This ancient dialogue with stone is teaching us how to build better at the scale of atoms. Perhaps the most profound frontier is not in the materials themselves, but in the cognitive systems they represent. How did societies with no central bureaucracy coordinate the movement of millions of limestone blocks? How did oral traditions maintain the precise recipes for bronze alloys across generations? Researchers in fields like complex systems theory and organizational psychology are now looking at these ancient projects as case studies in decentralized intelligence and robust knowledge transmission. The pyramid was not built by a single genius with a blueprint, but by a distributed network of specialized teams, quarrymen, transporters, ramp builders, setters, and finishers, all operating with a shared goal and a common unit of measurement. This system was remarkably resilient, able to adapt to setbacks and continue for decades. Studying its social architecture can offer clues for managing modern global projects, from responding to climate crises to coordinating international space exploration. Similarly, the guild system that protected and transmitted craft knowledge through apprenticeship presents a model for preserving complex, tactile skills in a digital age. How do we teach the intuitive judgment of a master smith or the feel of a perfect obsidian fracture? The answer may lie in blending ancient mentorship models with modern simulation technology, creating immersive learning that trains both the mind and the hands. The ultimate reverse engineering project is not of a tool, but of the human mind that created it. By understanding how our ancestors thought with and through materials, we gain insight into our own cognitive potential. This research reframes the past not as a sequence of artifacts, but as a vast, open-source library of solved problems. The solutions are written in the language of chemistry, physics, and social cooperation, waiting for us to learn how to read them with new eyes. The legacy of bronze, obsidian, and limestone is no longer locked in museum cases. It is active, informing the design of smarter materials, more sustainable cities, and more resilient human systems. The future is being built, in part, by listening to the whispers of the oldest stones. The whispers of ancient workshops are now being amplified by electron beams and X-ray scans. We have moved beyond simply admiring these artifacts in glass cases. Today, they are being placed inside scanning electron microscopes and bombarded with X-ray fluorescence, not to date them, but to dissect their very souls at a molecular level. This is archaeology's new frontier, a high-tech phase where the past becomes a living laboratory for the future. Scientists from the fields of materials science and engineering are now in constant dialogue with archaeologists, forming interdisciplinary teams with a shared goal to reverse engineer antiquity. They are not seeking to copy, but to comprehend the hidden intelligence within these old materials, intelligence that can solve modern problems. Take the green patina on a bronze statue. To a chemist, this corrosion is a complex story of environmental interaction. By analyzing the exact crystalline structure of these corrosion products, researchers can understand how certain ancient alloys resisted decay. This knowledge is directly applied to developing smarter, more protective coatings for modern steel bridges, ship hulls, and even the delicate circuitry inside our electronics. The goal is to give our metals the same longevity that some bronze artifacts have demonstrated over millennia. The conversation gets even finer at the nanoscale. The obsidian blade's legendary sharpness is no longer just a historical footnote. It is a blueprint. Under powerful microscopes, scientists map the nanostructure of that perfect conchoidal edge, studying how the glass fractured to create a surface only a few atoms thick. This research informs the design of next-generation cutting tools, from industrial blades that stay sharper longer to surgical instruments that minimize tissue trauma. Some teams are even experimenting with creating synthetic materials that mimic obsidian's fracture behavior, aiming for a new class of super-hard, predictable ceramics. Perhaps the most impactful dialogue is happening with the humblest of materials, ancient lime plaster and mortar. For years, researchers marveled at the self-healing properties of Roman concrete in seawater. Now, by deconstructing its chemistry, they've unlocked the principle. The Romans used reactive volcanic ash, which created crystalline structures that filled cracks as they formed. Modern materials scientists are using this ancient recipe as inspiration to design new, eco-friendly building materials. They are formulating cements that incorporate industrial byproducts like fly ash, which not only reduces waste but can also actively absorb carbon dioxide from the atmosphere as they cure. This turns the very act of construction into a climate solution, a principle learned from 2,000-year-old harbors. This interdisciplinary work fundamentally changes the value of the past. The technological legacy of bronze, obsidian, and limestone is no longer a static exhibit in the Museum of Human History. It has become an active research and development resource, a vast, open-source library of solved problems written in the language of physics and chemistry. Every artifact, from a corroded coin to a flake of glass, is now a potential patent for a better future, waiting for us to learn its language. That journey through time is not just a story of objects, but a map of the human mind itself. We have traveled from the smelting pits of the Bronze Age to the volcanic flows that birth obsidian, and to the quarries that provided the stone for humanity's first skyscrapers. The legacy hidden within bronze, obsidian, and limestone is multifaceted, a rich tapestry woven from threads of empirical discovery, sophisticated engineering, cognitive development, and deep cultural meaning. These materials show us with stunning clarity that our ancestors were not primitive beings waiting to become technologically advanced. They already were, operating at the very peak of possibility within their world. Their minds were just as sharp, their curiosity just as fierce, and their capacity for innovation just as profound as our own. They simply worked with a different set of ingredients, facing the same fundamental challenges of survival, expression, and the desire to leave a mark. Their quiet revolutions in standardization, specialization, and synthesis do not echo faintly from a distant past. They resonate powerfully in our laboratories and workshops today. The principle of combining materials to create new properties, first seen in the bronze alloy, is the bedrock of modern composites like carbon fiber. The specialized toolkit of the ancient craftsperson has evolved into the vast, interconnected ecosystem of modern professions. The intuitive grasp of physics demonstrated by megalithic builders informs our most advanced architectural software. The past is not a separate country, it is the foundation upon which we stand. As we now face our own profound material challenges, from creating sustainable cities to designing circular economies, perhaps the greatest lesson is to look back not with condescension, but with humility and curiosity. We must recognize that the seeds of future solutions may lie patiently encoded in the enduring stones and metals of our shared past, waiting for us to ask the right questions. Let this exploration change how you see the world around you. That old stone wall in a historic city center is no longer just a wall. It is a page from a manual on communal labor and geological understanding. The bronze statue in a museum case is not a static artifact, but a frozen moment of alchemical transformation and symbolic power. Every fragment, from a simple flint arrowhead to a polished jade amulet, holds a piece of this incredible, continuous story of human ingenuity. It is a story that belongs to all of us, written in the universal language of material and mind. If this journey into our technological roots resonated with you, consider subscribing for more deep dives into history's hidden codes. We would love to hear your thoughts, so share which ancient material or innovation amazes you most in the comments below. The conversation across millennia continues, and your voice is